Right now, the space between your fingers and the surface holding this device sits at a temperature just a few degrees above the coldest anything in the known universe can ever be. The void between galaxies, that vast, lightless expanse separating one island of stars from the next, hovers at approximately 2.7 Kelvin, nearly absolute zero. Nearly the point at which all thermal motion ceases and matter itself becomes as still as physics allows anything to become. But here is what almost everyone gets wrong about that number. The universe is not cold the way a winter morning is cold. Cold, in the ordinary sense, requires a medium. It requires air molecules slowing down, heat transferring from your skin into the surrounding environment. A thermodynamic exchange between your body and the world around it. Step outside on a January night, and the cold you feel is an active process warmth being pulled from you into the atmosphere. The sensation of cold is the sensation of losing something. Space does not work that way. In the vacuum between stars, there is almost nothing to pull warmth from you at all. If you were somehow suspended in open space without a suit, you would not freeze quickly. You would overheat. The human body generates more heat than the near vacuum of space can efficiently draw away. The danger in space is not the cold. It is the silence of the void, the near total absence of any medium capable of carrying your body's excess heat outward. The 2.7 Kelvin of the cosmic background is the temperature of the radiation field threading through space, not of any substance that could reach in and take something from you. The number that began this video, the flatness of the universe, measured to within half a percentage point by the Planck satellite after 4 years of observation, works in exactly the same way. It sounds like a fact about size. It sounds like the universe is simply very, very large, and someone has gone to the trouble of confirming it. But the number, when you follow what it actually means through the chain of physical reasoning, says something far stranger than that. It says the universe may not be a finished object at all. It says the structure of space, under the simplest and most consistent reading of everything we have measured, extends without boundary in every direction, not as a metaphor, not as a poetic flourish about vastness, but as a literal geometric fact with specific mathematical content. And once you accept that geometric fact, a quieter and more unsettling conclusion follows from it as automatically as a shadow follows a light source. If the universe is spatially infinite, and the laws of physics operate the same way everywhere, both assumptions the cosmological community treats as the working default, then somewhere, at a distance, the mathematics can calculate precisely, there is another version of the space you currently occupy. Another room with the same arrangement of objects. Another body in the same posture. Another mind carrying the same thought you are carrying right now. Not as a possibility, not as a speculation, as a statistical certainty that falls out of the arithmetic of infinite space and finite physical configurations. If this is the kind of journey that interests you, one that follows the actual science where it leads, without softening what the equations say, consider subscribing and leaving a like. It costs nothing, and it genuinely helps this channel continue making these videos. Now, make yourself comfortable. We are going to take this slowly, and we are going to go somewhere most cosmology discussions stop just short of reaching. Let us begin. The chair beneath you, or the mattress, or the floor, wherever your body is resting in this moment, take a few seconds and become aware of the space immediately around you, not the objects in the space itself, the gap between your hand and the nearest wall, the air inside your chest as you breathe in, the cubic centimeters of atmosphere between your face and the ceiling. All of that space, every invisible portion of it, was once part of something unrecognizable. Approximately 13.8 billion years ago, the region of space that today contains everything you can see in every direction, every star, every galaxy, every structure in the observable universe was undergoing a process of expansion so extreme that no analogy drawn from ordinary experience can fully carry it. The word expansion is technically correct but emotionally inadequate. Expansion, in the everyday sense, suggests something getting bigger at a comprehensible rate. A balloon inflating, a city growing, a fire spreading. What happened in the earliest moments of what we call the universe was not like that. The region of space that would eventually become our observable patch was doubling its volume on timescales of approximately 10 to the power of negative 34 seconds. That is a decimal point followed by 33 zeros and then a 1. The doubling was not happening once or twice or a few hundred times. It was happening continuously, stacked upon itself, exponential upon exponential, for a period that in human terms is essentially instantaneous, but that in terms of its physical consequences was sufficient to take a region of space smaller than a single proton and stretch it into something vast enough to become the universe we now inhabit. This process has a name. It is called inflation. It was proposed in its original form by a physicist named Alan Guth in 1980, refined by André Linde in 1982, and confirmed by every major cosmological measurement undertaken in the 4 decades since. The Cosmic Background Explorer satellite in 1992, the Wilkinson 2003, the Planck satellite in 2013, and again in 2018. Every time we have pointed our most sensitive instruments at the sky and asked what the earliest moments of the universe looked like, the answer has been consistent with inflation. This is the conventional story, a dramatic opening act of exponential expansion, followed by a transition into the slower, more familiar expansion we observe today, followed by the gradual emergence of matter and radiation and stars and galaxies, and eventually a planet with a thin film of life on its surface, and within that film, a species capable of reconstructing the story of its own origins. The story, as usually told, ends at the transition. Inflation happened, then it stopped. Then everything we see followed from the stopping, end of opening chapter. But there is a sentence that appears in almost no introductory treatment of this subject, and the absence of that sentence is the reason this video exists. The inflation that produced our local region of space did not stop everywhere. It only stopped here, just past the boundary of what any telescope we could ever build will ever be able to see at the edge of what cosmologists call the cosmic event horizon, sitting at a distance of approximately 16.5 billion light-years from where you are right now. The physics that operated in the first fraction of the first second of our universe's local history is, by the mathematics of our best theory, still operating, not as a relic, not as a remnant, as an ongoing process running at full intensity, producing new regions of space at a rate that dwarfs anything our observable universe contains. The engine that made us is still running. That sentence is the spine of this video. Every chapter that follows is an attempt to put enough structural support under that sentence that by the time we reach the end, it no longer sounds like a metaphor. Because it is not a metaphor. It is the literal technical content of the leading theory of the universe's earliest moments, supported by the most precise cosmological measurements in human history, defended in public by the community of physicists who built the theory and tested it against the data. We are going to walk through what that means carefully. We will start with a concept that almost everyone who thinks about it carries incorrectly the meaning of the word infinite, and why the cosmological version of that word is stranger and more specific than the everyday version. Then we will walk into the Planck measurement itself, the actual number, what it measures, what it implies. Then we will trace the inflation story from Guth's original notebook realization through Linde's refinements, through the confirmation that rolled in across 4 decades. Then we will arrive at the moment in 1986, when Linde, running his own equations forward, found a result he had not been looking for, a result the equations kept producing, regardless of whether he wanted them to. We will look at the boundary that separates what we can see from what we cannot. We will look at the one anomaly in the observational record that might be a fingerprint of what lies beyond that boundary. We will look at the public debate over whether any of this is real science at all, and at how the mainstream community responded to that challenge. We will look at what a flat infinite universe implies about the existence of other versions of you, without invoking any speculative extension beyond the simplest reading of what we already measure. And then we will name the engine. We will describe exactly what it is, what it does, why it has no off switch, and what it means to be sitting in a chair on a planet inside a bubble that the engine produced, while the engine continues its work in volumes of space we will never reach. The universe is not large. Large is not the right word. Large is a word that belongs to a different category of claim than the one this video is making. The universe is, by the best measurement we have, and the most straightforward interpretation of that measurement, without boundary. And it is without boundary not because it was always that way, not because it came into existence that way, but because the process that created the region we call home has not finished creating. The process is ongoing. The universe is unfinished. We will come back to that phrase many times. The first time it will feel like a metaphor. By the end, it will feel like a description. Are you ready? Let us begin. When the word infinite enters a conversation about the universe, most people perform the same mental gesture without realizing they are doing it. They reach for a size image. They picture something like the ocean already vast, already beyond the comfortable grasp of ordinary perception, and then they imagine that ocean extended outward without a coastline anywhere. Stars and galaxies where the water would be, darkness where the surface would be, and the whole arrangement continuing in every direction without ever arriving at an edge or a wall or a place where the inventory of things runs out. This is a natural picture. It is also, in nearly every way that matters, the wrong one. The error is not in the image of vastness. The universe is vast, and imagining it as something that continues without limit is not by itself misleading. The error is in treating infinite as a size word, as though it were simply the largest entry at the end of a list that goes small, medium, large, very large, enormously large, and then infinite at the end as the final superlative. Infinity in that picture is just bigness taken to its logical extreme. It is the universe being as large as something can be. Mathematics does not use the word that way. In mathematics, infinite is not a position on a size scale. It is a statement about the structural properties of a collection or a space, specifically about whether that collection can be exhausted by a counting process. A set is infinite, if and only if, no matter how far you count through it, there are always more elements remaining. This is not a statement about how impressive the set is. It is a statement about the kind of thing the set is. You can have an infinite collection that fits inside a space 1 inch across. The points on a line segment 1 inch long form an uncountably infinite set. Not because the inch is secretly very large, but because the mathematical structure of continuous space contains more points than any counting process can reach, regardless of the physical length of the interval. When cosmologists say the universe may be spatially infinite, they are making a claim in this set allegory, a structural claim, not a size claim. They are saying that the three-dimensional geometry of space has a particular topological character, that a traveler moving in a straight line through this geometry would never arrive at a boundary and would never, after traveling far enough, return to the point of departure. The claim is about the global shape of space, about whether the fabric of the universe wraps back on itself or extends without limit, about the answer to a question in the topology of three-dimensional manifolds, rather than an answer to the question of how many cubic light-years of space there are. The distinction between these two kinds of claim matters because they point in different directions when you try to reason about them. Consider a universe shaped like the three-dimensional analog of the surface of a sphere. On the surface of an ordinary sphere, the surface of the Earth, for example, you can walk in any direction indefinitely without ever reaching an edge. The Earth's surface has no boundary in the geographical sense, no wall, no cliff at the end of the world beyond which the surface stops, and yet the total area of that surface is finite. You can calculate it precisely, approximately 510 million square kilometers. The finiteness and the absence of a boundary coexist without contradiction because the surface curves back on itself. Walk far enough in any direction and you return to where you began. A universe with the three-dimensional equivalent of this geometry, technically called a three-sphere, would be finite in total volume while being unbounded in the traveler's experience. You could move through it forever without hitting a wall. You would eventually return to your starting point, but the return journey would require traveling a distance determined by the curvature of the space, which could in principle be so large that no civilization could survive long enough to complete it. Such a universe would be finite. It would not be infinite in the mathematical sense, and it would not match the picture most people carry when they imagine an infinite universe, because the picture most people carry is about size, and this universe is not small. This is an important case to hold clearly in mind, because it represents the alternative to the conclusion the Planck measurement points toward. A closed, finite universe is a real physical possibility. It is consistent with general relativity. It is consistent with the qualitative character of what we observe. What it is not consistent with, or rather, what the simplest reading of the data does not favor, is the precise quantitative measurements of spatial curvature we have made. There is a second error people make about infinity, and it is more consequential than the first. It is the assumption that the question of whether the universe is infinite is the kind of question that could in principle be settled by going to look. The intuition is that if we could only build telescopes powerful enough, or send probes fast enough, or wait long enough, we could eventually determine whether the universe ends somewhere or continues forever. Given enough time and enough technology, surely we could just find out. This is not possible, and the impossibility is not a technological limitation. It is a structural feature of our situation that no engineering advance can change. We are enclosed within a causal sphere defined by two quantities, the speed of light and the age of the universe. Light moves at a fixed speed. The universe has existed for a fixed period of time. Therefore, the light that has had time to reach us since the universe became transparent, approximately 380,000 years after the beginning of what we call the Big Bang, places a hard limit on how far into the universe we can see. This limit is called the particle horizon, and it sits at approximately 46.5 billion light-years in every direction. The number is larger than 13.8 billion light-years. The age of the universe multiplied by the speed of light, because space itself has been expanding throughout the journey of the light that is now reaching us, carrying distant objects farther away, even as their light traveled toward us. Beyond the particle horizon, there is more universe. The prevailing model of cosmology does not suggest the universe ends there, but no light from beyond that boundary has yet reached us. No signal of any kind, traveling at any speed permitted by physics, has had time to make the journey. The region beyond the particle horizon is real, in the sense that the cosmological model does not place a wall there, but it is permanently inaccessible to direct observation from our current position in time. The cosmic event horizon is a related but distinct boundary, and for the purposes of this video, it is the more important of the two. The event horizon sits at approximately 16.5 billion light-years closer than the particle horizon, and it marks something different. It marks the boundary beyond which any signal sent from our location today will never arrive at its destination. Not because there has not been enough time, but because the accelerating expansion of space driven by dark energy is carrying everything beyond that distance away from us faster than any signal could close the gap. The event horizon is a boundary on the future, not the past. It is the limit of what we can ever affect, or be affected by going forward, rather than the limit of what we have been able to see so far. Beyond the event horizon, no observation we make and no measurement we take will ever return information about what lies there. The wall is not technological, it is causal. It is built into the structure of an accelerating universe by the same physics that governs everything else we observe. So, why do cosmologists discuss whether the universe is infinite at all, if direct observation cannot reach far enough to settle the question? The answer is that the question can be approached from a different direction. Rather than trying to look far enough outward to find a boundary or confirm the absence of one, we can measure the local geometry of space with precision and then apply a principle about uniformity to extend the local measurement to a global conclusion. This principle is called the cosmological principle, and it states that the universe, on sufficiently large scales, looks the same from every location. No point in the universe is privileged. No region has a fundamentally different structure from any other region when you average over scales large enough to smooth out local variations like galaxy clusters and voids. The universe is, on the largest scales, homogeneous, the same density everywhere, and isotropic, the same in every direction. The cosmological principle is an assumption. It is not a measurement. It is consistent with everything we have observed. It is motivated by the theoretical prediction of inflation, which smooths out pre-existing inhomogeneities, and it is mildly tested by large-scale structure surveys, which show the universe becoming increasingly uniform as we probe larger and larger scales. But it has not been proven in any strict empirical sense. It is the working assumption of modern cosmology adopted because it is consistent with the data and because the alternative, a universe with privileged special regions, would require explaining what makes those regions special and why we happen to be in one. If the cosmological principle holds, if the universe is genuinely the same everywhere on large scales, then the geometry we measure locally is the geometry of the universe globally. The local curvature of space is the universal curvature of space. And the local curvature, when we measure it with the most precise instruments we have ever built, comes back as something very close to zero. Flat. That is where the measurement lives, not in the vast invisible expanses we cannot reach. In the local geometry of the space we inhabit, characterized with a precision of 0.5 percentage point by 4 years of satellite observation, the local geometry is flat. Under the cosmological principle, the global geometry is flat, and a flat geometry, in the language of cosmological topology, does not close back on itself. It does not return the traveler to the starting point. It extends, by the mathematics of the relevant differential geometry, without boundary. Flat means infinite, not metaphorically, not approximately, in the precise technical sense in which the word infinite has meaning in the equations of general relativity applied to a homogeneous, isotropic spacetime with zero spatial curvature. We have not measured infinity. We have measured something that implies infinity, under an assumption that the community treats as the working default. The chain of inference is real, the measurement is real, and the conclusion that the universe is, by the simplest reading of the available data, spatially infinite, is not a fringe position or a speculative extension. It is what the standard textbooks of modern cosmology say when they discuss the results of the Planck satellite. We are going to look at that measurement now. We are going to look at the actual number, the actual satellite, the actual physical procedure that produced the conclusion that the universe is flat. Because sitting with the measurement itself rather than simply with the conclusion changes how the conclusion feels. The measurement is precise. It is not poetry. Someone built a machine, put it in space, pointed it at the sky for 4 years, and read out a number. The number, within the uncertainties of the measurement, is zero. The curvature of the universe is zero. That is where we go next. In March of 2013, a European Space Agency satellite called Planck released the first of what would become 2 landmark sets of measurements. The second and final release came in 2018 in a paper formally titled Planck 2018 Results, Cosmological Parameters, published in Astronomy and Astrophysics, Volume 641, Article A6. It is among the most cited documents in the history of modern cosmology, and buried within its dozens of carefully derived numbers describing the density of ordinary matter, the density of dark matter, the age of the universe, the rate of its expansion is a single parameter that quietly changed the default assumption of the field regarding the most fundamental question one can ask about the shape of space. The parameter is called the spatial curvature density, written in the standard notation as omega sub k. The Planck 2018 measurement of this parameter is 0, plus or minus 0.005. 0 to within 0.5 percentage point. To understand what this number means, you need to understand what it is measuring. In Einstein's general theory of relativity, the geometry of three-dimensional space is not fixed in advance. Space can curve. The curvature is not a metaphor. It is a precise mathematical property of the metric that describes distances between points, and it has observable consequences. The way light bends around massive objects, the way clocks tick at different rates at different gravitational potentials, the way the angles of a very large triangle add up to more or less than 180 degrees depending on where the triangle is drawn. Space curves, and the curvature is measurable. For the universe as a whole, the curvature can take one of three basic forms. Each form corresponds to a different global geometry, with different physical and topological implications. The first possibility is positive curvature. A universe with positive curvature is the three-dimensional analog of the surface of a sphere. Draw a triangle anywhere in such a universe, a triangle whose sides are perfectly straight lines, following the natural geodesics of the curved space, and the interior angles will add up to more than 180 degrees. Travel far enough in any direction, and you will eventually return to your starting point. The universe is closed. It has a finite total volume. It has no boundary in the sense of a wall or an edge, but it wraps back on itself the way the surface of the Earth wraps back on itself. A positive curvature universe is finite and unbounded simultaneously. The second possibility is negative curvature. A universe with negative curvature has the geometry of a saddle surface extended into 3 dimensions. Draw a triangle in such a space, and the interior angles add up to less than 180 degrees. Travel in any direction and you never return to your starting point, because the geometry opens outward rather than curving back. A negatively curved universe is infinite and open. The third possibility is zero curvature, a flat universe. Draw a triangle anywhere in such a space, and the interior angles add up to exactly 180 degrees, as Euclid described, as every geometry student learns in school. The geometry of flat space is the geometry of an ordinary three-dimensional coordinate system extending without limit in every direction. Travel in any straight line and you never return. The space does not close back on itself. Under the standard topological assumption that the universe has the simplest possible global topology consistent with its local geometry, a flat universe is spatially infinite. The Planck measurement says omega sub k is 0. The curvature is flat to within the precision of the measurement. Now, it is important to be precise about what this means and what it does not mean, because cosmology is a field with a history of conclusions stated more confidently than the data strictly supports, and the curvature measurement is subtle enough to deserve careful handling. The measurement is consistent with exactly 0 curvature. It is also consistent within its error bars with a very small positive curvature and with a very small negative curvature. The measurement does not rule out a closed universe. What it does is place a lower bound on the size of any closed universe that could produce data consistent with what Planck observed. If the universe is positively curved and therefore finite, its geometry is that of a 3-sphere, a sphere in 4-dimensional space whose surface is the 3-dimensional universe we inhabit. The radius of that 3-sphere is what the curvature measurement constrains. The Planck data says that if such a radius exists, it must be at least approximately 250 times larger than the radius of the observable universe. That is roughly 11,500 billion light-years, a number so large that from inside our observable patch, the curvature is indistinguishable from 0. Think of it this way. If you were an ant living on a sphere the size of the Earth, and you could only see a patch of the surface a few centimeters across, the curvature of that patch would be so slight as to be unmeasurable with any tool available to you. The surface would appear flat. You would have no observational access to the global shape of the sphere you were standing on. This is approximately the situation we are in. Our observable patch may be so small relative to the total extent of the universe, whether finite or infinite, that the local geometry appears flat regardless of what the global geometry actually is. This honest acknowledgement of the measurement's limits does not undermine the conclusion, it refines it. The conclusion is not that the universe is definitely infinite. The conclusion is that the universe is at minimum vastly larger than anything we can observe, and that under the simplest interpretation of the data exact flatness, standard topology, the universe is infinite. These are two different claims, and both of them follow from the measurement. The first is the conservative reading. The second is the default reading of the working cosmological community. There is a more complicated reading of the Planck data that deserves attention before we move forward, because it represents the most serious challenge to the flat universe consensus, to emerge from the data itself rather than from theoretical objections. In 2020, a team of 3 physicists, Eleonora Di Valentino, Alessandro Melchiori, and Joseph Silk, published a paper in Nature Astronomy, Volume 4, page 196, arguing that the Planck dataset contains an internal tension that the standard flat universe interpretation does not resolve cleanly. Their argument centered on the gravitational lensing measurements encoded in the Planck data. Gravitational lensing is the bending of light paths by the mass of large structures. The cosmic microwave background, the ancient light we use to measure the universe's geometry, carries imprints of this lensing as it passes through the large-scale structure of the universe on its way to our detectors. The amount of lensing encoded in the Planck data can be used as an independent probe of the universe's geometry, separate from the primary temperature fluctuation measurements. The Di Valentino team found that the gravitational lensing signal in the Planck data is stronger than a flat universe predicts. A stronger lensing signal indicates that space is focusing light more aggressively than flat geometry allows, which is the signature of positive curvature of a universe that is closed rather than flat. When they analyzed the lensing data independently, they found a preference for a closed universe with a curvature parameter of approximately -0.04 at a statistical significance of 99.985%. If you take only this component of the Planck data, the universe is closed, it is finite, and it is only about 30 times larger than the observable patch enormous, but not infinite. This finding caused genuine discussion within the cosmological community when it was published, because it came from the Planck data itself, not from some independent or competing measurement. The resolution, such as it is, comes from combining the Planck data with independent cosmological measurements. Baryon acoustic oscillation data from the Sloan Digital Sky Survey, a survey of hundreds of thousands of galaxies that uses the characteristic scale of density fluctuations in the early universe as a standard ruler strongly favors a flat universe. When the Planck lensing data is combined with these baryon acoustic oscillation measurements, the tension disappears. The combined dataset is consistent with flatness. The preference for a closed universe in the lensing-only Planck analysis appears to be a statistical artifact that vanishes when the full picture of cosmological observations is taken into account. The majority of working cosmologists treat the lensing tension as a systematic effect within the Planck data, a sign that some aspect of the measurement or the modeling is not perfectly calibrated, rather than a genuine signal of positive curvature. A minority continue to treat it as a meaningful hint. The data does not definitively resolve the question, but the weight of the full observational record falls on the side of flatness. There is a number that can help make the flatness measurement feel more concrete. Consider what it means to measure an angle. When you draw a triangle on a flat piece of paper, the 3 angles always add up to exactly 180 degrees. This is a theorem of Euclidean geometry that holds precisely because the paper is flat, its curvature is 0. Now imagine measuring the angles of an enormous triangle drawn across the universe itself, with sides hundreds of millions of light-years long. If the universe has positive curvature, the angles will add up to more than 180 degrees. If it has negative curvature, they will sum to less. If it is flat, they will sum to exactly 180. The Planck measurement is essentially this experiment, conducted using features in the cosmic microwave background as the vertices of the triangle. The cosmic microwave background contains a characteristic scale, the distance sound waves traveled in the early universe before matter and radiation decoupled, approximately 380,000 years after the beginning. This scale, called the sound horizon, is encoded in the angular size of the temperature fluctuations we observe in the CMB. We know the physical size of the sound horizon from independent measurements. We can measure its apparent angular size on the sky. From these 2 numbers, physical size and apparent angular size, we can infer the geometry of the space the light has traveled through on its way to us. The result of this measurement is that the angles add up to 180 degrees. The universe is flat, not within a few percent, not within 1%, within half of 1%. The Planck team was careful in how they stated this conclusion. They noted the uncertainties. They noted the assumptions required to translate the curvature measurement into a claim about global geometry. They noted the cosmological principle and the topological assumptions embedded in the analysis. They did not announce that the universe is infinite. They reported a number, omega sub k equals 0 plus or minus 0.005. But in the conclusion sections of the cosmological textbooks updated since 2013, the implication is stated plainly. A flat universe under the cosmological principle is spatially infinite. The geometry does not close. The topology does not wrap. The space extends. There is something unusual about sitting with this measurement as a human being rather than as a technician or a theorist. Someone built a satellite. They launched it to a gravitationally stable point in space, 1.5 million kilometers from Earth. They cooled its detectors to within a fraction of a degree of absolute zero so that the satellite's own thermal emission would not drown out the faint signal they were trying to detect. They let it scan the entire sky repeatedly over 4 years, accumulating maps of the temperature of the cosmic microwave background at a precision of 1 part in 100,000. They processed the data through months of analysis, and at the end of that process, they extracted a number. The number was 0. Not approximately 0. Not 0 with large uncertainties. 0 within half a percentage point, with tight enough error bars that the curvature, if it exists at all, is too small to affect the behavior of the universe on any scale we can probe. 0 curvature, flat, infinite, under the standard assumptions. That is the measurement. That is what we know. But the measurement tells us what the universe is. It does not tell us why. It does not explain why the geometry of space came out flat rather than curved. It does not explain why the curvature parameter, which could in principle have taken any value, landed so close to 0 that we cannot distinguish it from 0 with 4 years of satellite data. That question, the question of why, is what the next chapter addresses. The answer has a name. The answer is the same theory that explains why the cosmic microwave background is smooth, why magnetic monopoles are absent from the observable universe, why the density of matter is as uniform as it is across billions of light-years of space. The answer is what Alan Guth realized in a calculation that he described in his notebook as a spectacular realization in December of 1979, working at the Stanford Linear Accelerator Center on a problem that had nothing obviously to do with the shape of the universe. The answer is inflation. And inflation, when you follow it carefully, does not just explain why the universe is flat. It tells you something about what is still happening right now, just beyond the boundary of what that Planck satellite could ever see. Something the equations kept producing, even when the person running the equations would have preferred they did not. That is where we go next. To understand why the universe is flat, and to understand why that flatness points towards something stranger than flatness itself, you have to understand the theory that explains it. And to understand that theory, you have to understand the problem it was invented to solve, because inflation was not built to explain flatness. Flatness was a consequence that emerged from a theory built to solve something else entirely. The flatness explanation came along for free, which, in theoretical physics, is one of the most powerful signals that a theory is pointing at something real. The year is 1979, December. A young physicist named Alan Guth is working at the Stanford Linear Accelerator Center. In an office that was not originally his, he was a postdoctoral researcher moving between institutions on the kind of temporary appointment that defines early academic careers in physics. He was not working on cosmology in any direct sense. He was working on grand unified theories, a family of theoretical frameworks attempting to unify 3 of the 4 fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force, into a single mathematical structure that would operate at extremely high energies. The specific problem he was working on was a technical one involving the behavior of quantum fields during phase transitions in the very early universe. As the universe cools from an extremely hot, dense state, quantum fields that were unified at high temperatures separate into distinct forces at lower temperatures, in a process analogous to water freezing into ice. a phase transition where the symmetry of the high-temperature state is broken into the lower symmetry configuration of the cooled state. Guth was working through the mathematics of what happens when such a field gets temporarily trapped in a configuration that is not the true lowest energy state, what physicists call a false vacuum, before tunneling or transitioning into the true ground state. He wrote a calculation. The calculation showed that if a scalar field, a quantum field with a particular kind of potential energy landscape, became trapped in a false vacuum state in the very early universe, that field would behave in a specific and striking way under the equations of general relativity. A region of space dominated by the constant energy density of a false vacuum expands exponentially, not linearly, not as a power law, but as a true exponential, doubling its volume on a fixed timescale, then doubling again, then again. The rate of volume increase itself increasing with every doubling. Guth wrote in his notebook, in the margin of the calculation, the phrase spectacular realization. The realization was this: an early period of exponential expansion, driven by a false vacuum field, would solve three distinct problems that had been nagging at the standard hot Big Bang model for years, problems that the model could describe but could not explain. Three separate puzzles, each requiring its own separate and seemingly unrelated answer, all dissolving simultaneously under the single theoretical move of postulating a brief, early period of exponential expansion. The first problem was the horizon problem. The cosmic microwave background, the ancient thermal radiation released when the universe cooled enough for electrons and protons to combine into neutral atoms, approximately 380,000 years after the Big Bang, has the same temperature in every direction we look, to within 1 part in 100,000. This uniformity is extraordinary. It means that regions of the early universe that are now on opposite sides of the sky, separated by angular distances of 180 degrees, had the same temperature at the moment the CMB was released. In the standard Big Bang model, without inflation, this uniformity is inexplicable. Consider two patches of the CMB on opposite sides of the sky. To have the same temperature, they must at some point have been in thermal contact close enough together, long enough, for energy to flow between them and equilibrate. But when you trace the history of those patches back through the expansion of the universe, under the standard model, they were never in causal contact. The distance between them, even in the earliest moments, exceeded the distance light could have traveled in the available time. No physical process could have carried information between them. No mechanism could have brought them to the same temperature. And yet, they are at the same temperature, to 1 part in 100,000. This is the horizon problem. The universe is smoother than any physical process in the standard model can explain. Inflation solves it completely, in a single step. If the entire observable universe, everything we can see in every direction, was once contained within a region small enough to have been in thermal equilibrium, and then that region was stretched by a factor of at least 10 to the power of 26 during an inflationary phase, the temperature uniformity we observe today is simply inherited. The smoothness was established before inflation began, when everything we now see was packed into a volume smaller than an atomic nucleus. Inflation stretched the smooth patch across the sky. The uniformity is not a coincidence. It is a remnant. The second problem was the flatness problem. We have just spent an entire chapter on the Planck measurement that found the universe to be flat to within half a percentage point. But the flatness problem existed long before Planck. The universe has been measurably close to flat for as long as we have been able to measure its geometry. And in the standard Big Bang model, flatness is not a stable condition, it is an unstable one. In a universe governed by ordinary matter and radiation without inflation, any small deviation from perfect flatness at early times grows with time. The universe does not naturally stay flat. If the curvature was slightly positive in the earliest moments, it would grow more positive as time went on, eventually causing the universe to recollapse. If it were slightly negative, it would grow more negative, causing the universe to expand so rapidly that matter could never clump into stars and galaxies. Flatness is the knife edge between these two outcomes, and staying on that knife edge requires extraordinary precision in the initial conditions. To produce the flatness we measure today flat to within half a percentage point, the universe at the Planck epoch, approximately 10 to the power of negative 43 seconds after the Big Bang, would have had to be flat to within 1 part in 10 to the 60th power, 1 followed by 60 zeros in the denominator, a precision so extraordinary that it is not a fine-tuning in the ordinary sense. It is a number whose required accuracy sits far outside the range of any plausible physical mechanism in the Standard Model. Inflation eliminates this problem by the same mechanism it uses to solve the horizon problem. Stretching space by a factor of 10 to the 26 flattens it. In the same way that inflating a balloon from the size of a marble to the size of a city would make the balloon's surface look flat to any observer, standing on it the curvature would be there, but it would be spread across such a vast area as to be locally invisible. Inflation takes whatever curvature the pre-inflationary patch had and dilutes it to unmeasurably small values. The flatness we observe is not a coincidence requiring miraculous initial conditions. It is the natural outcome of a universe that went through an inflationary phase, lasting long enough to do the job. The number of e-folds of inflation required to explain the observed flatness is approximately 60. An e-fold is a natural unit of exponential growth. 1 e-fold corresponds to a factor of e, approximately 2.718 in linear scale, or a factor of about 20 in volume. 60 e-folds of inflation corresponds to a linear expansion factor of roughly 10 to the 26. A region of space the size of a proton becoming, in less than 10 to the power of negative 32 seconds, something vast enough to contain everything we can see. The third problem was the magnetic monopole problem. Grand unified theories, the same family of theories Guth was working on when he made his spectacular realization, predict that as the early universe cooled through the energy scale of grand unification, it should have produced large numbers of a particular kind of exotic particle called a magnetic monopole. A magnetic monopole is an isolated magnetic charge, a north pole without a south pole, or a south pole without a north pole. Every ordinary magnet has both poles. Monopoles are theoretically predicted by grand unified theories as topological defects that form during symmetry-breaking phase transitions in the early universe. The predicted abundance of monopoles is staggering. Grand unified theories suggest that monopoles should be produced in sufficient numbers that they would today represent the dominant form of mass in the universe, far outweighing all ordinary matter, all dark matter, everything. If the standard Big Bang model is correct and grand unified theories are approximately right, monopoles should be everywhere. They should be detectable in cosmic rays. They should be detectable in ancient rock samples. They should be detectable in particle accelerators. No confirmed magnetic monopole has ever been observed. Physicists have searched for them in cosmic rays for decades. They have searched in deep Antarctic ice. They have searched in the rock record of the Earth's crust. They have run particle accelerators to energies approaching the grand unification scale. The confirmed detection count is 0. Inflation resolves this by dilution. If the universe underwent 60 or more e-folds of inflationary expansion after the monopoles were produced, the density of monopoles drops by a factor of 10 to the 78 or more. Whatever number of monopoles existed before inflation spreads them across a volume so vastly larger than what they occupied that the expected count within our observable patch falls to something close to 1 per observable universe, effectively 0. The monopoles are presumably still out there, somewhere in the infinite expanse of space. They are simply so thinly distributed that finding one by chance would require searching a volume of space entirely beyond our reach. 3 problems. 1 theoretical mechanism. The exponential expansion of a false vacuum-dominated region of space in the earliest fraction of the first second of the universe's existence. Guth published his original paper in Physical Review D, Volume 23, page 347, in 1981, under the title Inflationary Universe, a possible solution to the horizon and flatness problems. It is one of the most influential papers in the history of modern cosmology. Within a year of its publication, it had been read by nearly every working cosmologist and had begun reshaping how theorists thought about the earliest moments of the universe. But Guth's original version of inflation had a problem. The exit from the inflationary phase, the moment when the exponential expansion ended and the energy stored in the false vacuum was converted into the hot soup of particles and radiation that became the early universe, did not work cleanly. In Guth's original picture, inflation ended through a process of bubble nucleation. Regions of true vacuum would spontaneously form inside the false vacuum and expand, eventually colliding and merging to produce a uniform post-inflation universe. The difficulty was that the inflationary expansion itself was carrying these bubbles apart faster than they could collide. The merging never completed. The post-inflation universe would have looked like Swiss cheese isolated pockets of true vacuum, embedded in a still-inflating background of false vacuum, rather than the smooth, uniform universe we observe. This was a genuine obstacle. Guth knew it. He published his paper with the probably mathematic acknowledged, trusting that the broader community would find the solution. The solution came the following year, in 1982, from a Soviet physicist named André Linde. Linde proposed what he called new inflation, published in Physics Letters B, volume 108, page 389. In Linde's version, the scalar field driving inflation was not trapped in a false vacuum waiting to tunnel out. Instead, it started near the top of a very shallow potential, an energy landscape shaped like a gently sloping hill rather than a cliff with a valley at the bottom, and rolled slowly downward toward the minimum. The rolling was slow because the potential was nearly flat at the top, meaning the force pushing the field toward the minimum was very weak. The field crept downward while the region of space it inhabited inflated exponentially. When the field finally reached the minimum, it oscillated and transferred its energy to ordinary particles and radiation, a process called reheating, and the inflationary phase ended smoothly, everywhere, simultaneously, without bubbles. No Swiss cheese, no merger problem, a clean, uniform exit from inflation into a hot, dense, smooth early universe. Slow-roll inflation, the name given to the class of models in which the inflaton field rolls gradually down, a shallow potential became within a few years the standard framework for inflationary cosmology. It survived every observational test administered in the decades that followed. The COBE satellite in 1992 detected for the first time the tiny temperature fluctuations in the cosmic microwave background that inflation predicts density variations at the level of 1 part in 100,000, seeded by quantum fluctuations during the inflationary phase, and stretched by the expansion to become the seeds of all large-scale structure in the universe. The measurements matched the inflationary prediction. WMAP in 2003 refined the measurements to higher precision. Planck in 2013 and 2018 refined them further still. The scalar spectral index, the number characterizing the slight tilt in the spectrum of primordial density fluctuations, was predicted by standard slow-roll inflation to be slightly less than 1. The Planck 2018 measurement gives a value of 0.9649, plus or minus 0.0042. The agreement is precise. The prediction and the observation match at the level of a fraction of a percent. Inflation is not a speculative framework. It is the leading theory of the early universe, supported by quantitative predictions confirmed by multiple independent measurements across 4 decades of increasingly precise observation. When physicists discuss the early universe in peer-reviewed papers, in textbooks, in seminar rooms, they work within the inflationary framework as the default starting point. But the inflation story, as it is usually told, ends at the exit. Inflation happened. The field rolled down to the minimum. The energy became matter and radiation. The hot Big Bang took over. The rest of cosmological history unfolded from there. This ending is accurate for our local patch of space. It is the correct description of what happened here in the region that became our observable universe. The field reached the minimum here. The inflationary phase ended here. The hot Big Bang was the local consequence of that ending. What the standard telling does not include what the introductory courses skip over, and what the popular treatments almost universally omit, is the question of what happened everywhere else. Not everywhere in our observable universe, everywhere in the larger region that our observable universe is embedded within? That question has an answer. The answer comes from André Linde, working 4 years after his new inflation paper in 1986. The answer is the result this video has been building toward since the opening, and it is a result that Linde, when he first worked through it, did not welcome. The math produced it anyway. That is where we go next. André Linde, in 1986, was not a young theorist chasing a spectacular realization in someone else's office. He was an established figure in the inflationary cosmology community, the architect of new inflation, the physicist who had solved the exit problem that Guth's original model could not resolve. He had spent 4 years refining the theory he helped build, fitting its predictions against the emerging observational data, developing new variants that addressed new complications as they arose. In 1983, he had introduced one of those variants, a version of inflation he called chaotic inflation, published in Physics Letters B, volume 129, page 177. Chaotic inflation differed from new inflation in a subtle but important way. In new inflation, the inflaton field began in a carefully prepared state near the top of a shallow potential. The preparation required some explanation why would the field start there, rather than somewhere else. Chaotic inflation replaced this with a more natural starting condition. Rather than beginning in a specific prepared state, the inflaton field in chaotic inflation started with values distributed randomly across different regions of space, set by quantum fluctuations operating at the Planck scale. Different patches of the early universe began with different field values, and therefore different amounts of inflation. Patches where the field started higher inflated more. Patches where it started lower inflated less, or not at all. The picture was in some sense more honest than new inflation. It did not require explaining why the field began in a special state. It simply acknowledged that at energies approaching the Planck scale, quantum fluctuations would naturally produce a wide distribution of field values across different regions, and it asked what cosmological consequences followed from that distribution. By 1986, Linde had been living with chaotic inflation for 3 years. He understood its dynamics in considerable detail, and in 1986, working through a question about the long-term behavior of the inflaton field during the inflationary phase, he encountered a result he had not anticipated. The question he was examining concerned the quantum behavior of the inflaton field while inflation was actively occurring. In the classical description of inflation, the description that ignores quantum mechanics, the field simply rolls down its potential. It starts at a high value, rolls toward the minimum, and when it reaches the minimum, inflation ends. The rate of rolling is determined by the slope of the potential at each point. The steeper the slope, the faster the roll. The shallower the slope, the slower the roll, and the more inflation occurs before the field reaches the bottom. But the inflaton field is a quantum field. Quantum fields do not simply roll, they fluctuate. At every point in space, at every moment in time, the field value oscillates around its classical trajectory due to the inherent uncertainty built into quantum mechanics. In most circumstances, these quantum fluctuations are small, tiny corrections to the classical behavior that average out over time and over space, leaving the classical trajectory as a good description of the field's overall motion. During inflation, however, something unusual happens to these fluctuations. The same exponential expansion that stretches the space also stretches the quantum fluctuations. A fluctuation that exists on a scale smaller than the Hubble radius, the characteristic scale of the inflationary expansion gets stretched by the expansion until it crosses the Hubble radius and becomes frozen. The fluctuation stops oscillating. It becomes a fixed, classical displacement of the field value across a region of space. This freezing of quantum fluctuations into classical density variations is the mechanism by which inflation seeds the large-scale structure of the universe. The temperature fluctuations in the CMB that COBE detected in 1992 and Planck measured with exquisite precision in 2018 are the frozen remnants of quantum fluctuations stretched to cosmic scales by inflation. Linde was thinking about a specific consequence of this mechanism, At any given point in the inflating space, the quantum fluctuations are pushing the field in random directions. Sometimes the fluctuation pushes the field downward, in the same direction as the classical roll toward the minimum. Those regions complete inflation sooner. Sometimes the fluctuation pushes the field upward, against the classical roll, toward higher potential energy values. Those regions stay in the inflationary phase longer. The probability of an upward fluctuation in any given small region of space per unit time is determined by the dynamics of the theory. It depends on the shape of the potential and on the value of the field. For the kinds of slow roll potentials that inflation models typically employ, the probability is small at any given point. The classical roll dominates. Most regions, most of the time, are rolling downward toward the exit from inflation. But here is the crucial point that Linde was working through. The inflating regions where the field has fluctuated upward are not simply persisting longer than average, they are inflating more vigorously. A higher field value corresponds to a higher potential energy. A higher potential energy corresponds to a larger cosmological constant, in the effective sense that matters for the dynamics. A larger effective cosmological constant drives faster, exponential expansion. The regions where the quantum fluctuation has pushed the field upward are, in that same moment, expanding their volume faster than the regions where the field has continued rolling downward. This asymmetry between the rate at which upward fluctuated regions grow and the rate at which downward rolling regions complete inflation is the engine of eternal inflation. Linde was calculating whether the volume of regions still undergoing inflation grows faster or slower than the rate at which inflating regions are being consumed by the completion of the inflationary phase. The answer, for the simple slow roll potentials that characterize the most natural versions of chaotic inflation, was unambiguous. The inflating regions reproduce themselves faster than they are consumed. At every moment, some fraction of the inflating volume completes inflation and becomes a post-inflation patch, a bubble of ordinary expanding space, a Big Bang in the local sense, the beginning of a cosmological history like ours. But the volume of the remaining inflating background grows faster than the volume being converted into post-inflation patches. The inflating background is not shrinking, it is growing. The total volume of space still undergoing inflation increases exponentially with time, without limit, forever. Linde published this result in Physics Letters B, volume 175, page 395, in 1986. The paper's title was Eternally Existing Self-Reproducing Chaotic Inflationary Universe. It is one of the most consequential cosmology papers of the late 20th century, and the result it contains is precisely what the title says. The inflationary universe is eternally existing. It self-reproduces. The inflationary phase, once started, does not end globally. It produces local endings, the post-inflation bubbles, of which ours is one while continuing without cessation in the background. This is eternal inflation. The name is not rhetorical, it is precise. The inflation does not stop. In the inflating background in the regions where the quantum fluctuations have sustained the field at high values, where the volume growth continues to outpace the bubble formation, the exponential expansion goes on indefinitely into the future. New post-inflation bubbles form at a steady rate per unit of inflating volume, per unit of time. Each bubble looks from the inside like a complete universe, with its own Big Bang, its own subsequent expansion, its own cosmological history. From any external perspective from another bubble, or from the inflating background itself, the bubble is simply a local event in a vastly larger, ongoing process. There are accounts from people who were present in the cosmological community during this period that describe Linde's initial reaction to his own result with some ambivalence. He had not set out to discover that inflation was eternal. He had not been looking for a prediction that placed our universe as one bubble among an unbounded ensemble. He had been working through the dynamics of a theory he had helped build, expecting the equations to behave as they had behaved in every previous calculation. When they did not, when the volume balance came out wrong, when the inflating background turned out to grow faster than the bubbles could fill it, he did not have the option of choosing a different result. The mathematics does not accommodate the preferences of the mathematician. He published anyway. The math kept producing it. Linde was not alone in arriving at this conclusion. Alexander Vilenkin, working at Tufts University, had been developing related ideas about the self-reproduction of inflationary domains independently during the same period. Vilenkin's approach emphasized the quantum nucleation of inflationary universes from nothing, a framework in which the entire inflationary process begins as a quantum tunneling event from a state of zero energy. But his analysis of the dynamics of an inflating background led to conclusions consistent with Linde's. The inflating background, once established, does not terminate globally. It continues to produce new post-inflation regions while expanding the inflating background itself. By the early 1990s, eternal inflation was understood across the inflationary cosmology community as the expected generic behavior of inflationary models rather than a special feature of particular versions. Not every inflation model produces eternal inflation. There exist carefully constructed models with very specific potential shapes in which the inflationary phase ends everywhere simultaneously, without the quantum fluctuation feedback that drives eternal self-reproduction. But these models require a degree of fine-tuning that the simpler and more natural versions do not. The versions of inflation that match the observational data most cleanly, the slow-roll models with shallow potentials and spectral indices near but slightly below 1 generically produce eternal inflation. The self-reproduction is not a feature added to the theory by enthusiastic theorists. It is what falls out of the equations when you let them run without artificially constraining the dynamics. There is a subtlety in the eternal inflation picture that deserves careful attention before we move forward, because it bears on how we should think about our own position within the larger inflationary cosmos. Eternal inflation is future eternal. It does not stop. Once the inflationary phase is established in a region, the dynamics ensure that the inflating background continues to grow forever into the future. But eternal inflation is not past eternal. It had a beginning. This was established rigorously in 2003 by three physicists, Arvind Borde, Alan Guth, and Alexander Vilenkin, in a paper published in Physical Review Letters, Volume 90, Article 15131, under the title Inflationary Spacetimes Are Incomplete in Past Directions. The Borde-Guth-Vilenkin theorem, as it is known, proves that any spacetime in which the average rate of expansion has been positive throughout its history must contain a past boundary a moment before which the spacetime did not exist. The theorem applies to the eternally inflating background itself. Even though eternal inflation has no future end, it must have had a past beginning. The proof is elegant in its structure. It does not rely on any specific model of inflation. It does not depend on the details of the inflaton potential or the precise mechanism of bubble nucleation. It depends only on the average expansion rate being positive, a condition satisfied by any inflationary spacetime, and it shows that any past-directed path through such a spacetime, traced back far enough, eventually reaches a point where the spacetime description breaks down. The spacetime is geodesically incomplete in the past direction. There is a boundary. What lies at that boundary, what initiated the inflation that then proceeded eternally into the future, is not specified by the theorem. The theorem proves that the boundary exists, not what caused it. Some theorists invoke quantum tunneling from a previous state. Some invoke a quantum cosmology framework, in which the boundary represents the quantum origin of spacetime itself. The honest answer is that we do not know what initiated the inflationary process. The Borde-Guth-Vilenkin theorem tells us the process had a beginning without telling us what that beginning was. The asymmetry between past and future in the eternal inflation picture is worth sitting with for a moment, because it changes how we should orient ourselves within the larger story. We tend to think of ourselves as cosmologically old. We live 13.8 billion years after the Big Bang, after the event we treat as the beginning of everything. When we look at the night sky and see light that has traveled billions of years to reach us, we feel the weight of all that elapsed time behind us. We feel late. We feel like inhabitants of a universe that has been running for a long time and has a great deal of history already behind it. Eternal inflation inverts this orientation entirely. In the eternal inflation picture, the future of the inflating cosmos is unbounded. Every moment that passes, additional inflating volume is being created. Additional post-inflation bubbles are nucleating. The total number of bubble universes in existence, the total number of local Big Bangs that have occurred and will occur in the inflating background, grows without limit as time advances. By the logic of statistical reasoning, the vast majority of observers in an eternally inflating cosmos exist much later than we do. The typical bubble universe is not one of the first to nucleate. It is one of the ones produced after an enormous stretch of inflationary time, when the total volume of the inflating background has grown by factors impossible to write with standard notation. We are not late, we are extraordinarily early. We are among the first observers in a process that will continue producing observers and the universes that contain them for an unlimited time into the future. This is a difficult orientation to adopt, because everything about our experience suggests that we are living in a mature, late-stage universe. The stars are formed, the galaxies are organized. The cosmic microwave background has cooled to 2.7 Kelvin. Everything looks settled, evolved, far removed from the violent conditions of the earliest moments. But in the frame of the eternally inflating background, in the frame of the process that produced our bubble and continues to produce others, our bubble is a recent event. The process is young. The vast majority of what eternal inflation will ever produce has not yet been produced. We are not at the end of the story. We are in the opening pages, and in the regions just beyond the boundary of what we can ever see, just past the cosmic event horizon that seals our observable patch from the still inflating background. The process that produced our opening pages is writing new ones right now, at every moment, at rates that have no ceiling. The engine that made us is still running. We need now to understand the boundary that separates us from it. We need to understand the horizon, not the particle horizon that defines the edge of what light has reached us from, but the event horizon that defines the limit of what we can ever interact with going forward. Because the event horizon is where the story gets specific. It is the place where the eternal inflation prediction becomes a concrete claim about what exists in our actual physical neighborhood, just beyond the edge of what any telescope could ever show us. That is where we go next. The horizon that is not a wall. There is a boundary in cosmology that almost never receives the attention it deserves in popular treatments of the subject. It is not the edge of the universe. It is not the farthest point light has ever reached. It is not a wall in any physical sense. No traveler approaching it would see anything unusual. No instrument pointed in its direction would detect a change in the character of space. It exists as a mathematical surface defined entirely by the relationship between the speed of light, the rate of cosmic expansion, and the geometry of space-time in an accelerating universe. It is called the cosmic event horizon. And once you understand what it is, precisely what it is, not approximately, not poetically, the eternal inflation prediction stops being an abstract theoretical claim and becomes a concrete statement about the structure of our actual physical neighborhood. To understand the cosmic event horizon, you first need to distinguish it clearly from a different boundary that receives far more attention, the particle horizon. The particle horizon is the boundary of the observable universe in the most straightforward sense. It marks the farthest distance from which light has had time to reach us since the universe became transparent approximately 380,000 years after the Big Bang, when electrons and protons combined into neutral hydrogen and the universe went from opaque to clear. Light released at that moment from the most distant regions has been traveling toward us ever since, for 13.8 billion years. But the space those photons have been crossing has itself been expanding throughout their journey, stretching the distance between their origin and our detectors even as they traveled. The result is that the particle horizon sits not at 13.8 billion light-years, but at approximately 46.5 billion light-years in every direction, the co-moving distance to the most remote regions whose light has yet reached us, accounting for the expansion of space that occurred during the journey. Everything within the particle horizon is, in principle, visible to us. Not everything is visible in practice. Some regions are too faint or too redshifted for current instruments, but in principle, light from every point within the particle horizon has had time to reach us. The particle horizon is a boundary about the past. It marks the limit of what has had the opportunity to communicate with us across the history of the universe so far. The cosmic event horizon is a boundary about the future. It marks something entirely different, not the limit of what has reached us, but the limit of what ever will. The current proper distance to the cosmic event horizon, under the standard cosmological model with parameters refined by the Planck collaboration and subsequent surveys, including the Dark Energy Spectroscopic Instrument through 2025, is approximately 16.5 billion light-years. This number is smaller than the particle horizon, considerably smaller, and the physical meaning of the difference is precise. Any signal sent from our location today, any photon emitted, any radio wave transmitted, any gravitational wave released will, if its destination lies beyond approximately 16.5 billion light-years from us right now, never arrive. Not because there is not enough time, not because the signal is not fast enough, but because the accelerating expansion of space driven by dark energy is carrying everything beyond that distance away from us faster than the signal can close the gap. The expansion is not uniform, it accelerates, and at the current rate of acceleration, the expansion velocity of space at a distance of approximately 16.5 billion light-years from us exceeds the speed of light. This does not violate relativity. Nothing is moving through space faster than light. Space itself is expanding, carrying points within it along for the ride, and the rate at which distant points are being carried away from us by the expansion of space is, beyond a certain distance, greater than the speed at which a light signal moves through space. The signal chases, but the destination recedes faster than the pursuit can close the distance. The gap between signal and destination grows with time rather than shrinking. The event horizon is where this crossover occurs. At distances less than approximately 16.5 billion light-years, signals we send today will eventually arrive at their destinations. The expansion is not fast enough to prevent the light from closing the gap. At distances greater than approximately 16.5 billion light-years, signals we send today will never arrive. The expansion carries the destination away faster than the signal travels. The event horizon is the boundary between these two regimes. Now consider what this means for the eternal inflation prediction. Eternal inflation says that just beyond the boundary of what we can observe in the regions outside our causal sphere, the inflating background is still inflating. New post-inflation bubbles are continuously nucleating within that background. Each bubble is a local Big Bang, a universe with its own cosmological history, potentially its own physics, if the inflaton field settled into a different minimum of the potential landscape. There are, in the simplest eternal inflation models, an unbounded number of such bubbles that have already formed and will continue to form. If any of these bubbles existed within our cosmic event horizon, if any portion of the still-inflating background or any of the other post-inflation bubbles were within 16.5 billion light-years of us, we would expect to see evidence of their existence. The most direct evidence would be signatures in the cosmic microwave background, characteristic distortions in the temperature pattern produced by the gravitational influence or the direct collision of another bubble with ours. We will examine the search for such signatures in the next chapter. The absence of obvious such signatures, the fact that the CMB looks, over most of its sky, exactly like the smooth Gaussian random field that standard single bubble inflation predicts, is itself a constraint. It tells us that if other bubbles exist, they are not within our event horizon, they are beyond it, permanently. The event horizon is therefore the wall that separates us from everything the eternal inflation theory predicts exists beyond our local patch. Not a wall in space, but a wall in causality, a boundary beyond which no information about external bubbles, no light from the still inflating background, no signal of any kind carrying evidence of the ongoing process can ever reach us. This is where the eternal inflation prediction achieves its strangest character. The theory makes a specific, concrete, well-motivated prediction about what exists just beyond a specific distance from where you are sitting. The prediction is, an exponentially expanding background that has been inflating since before our Big Bang and will continue inflating forever, populated by an unbounded number of post-inflation bubble universes of which ours is one. The prediction follows from dynamics that are well understood. The prediction is a consequence of a theory that is confirmed by multiple independent observations. And the prediction is permanently untestable from where we stand, not because our instruments are insufficient, but because the structure of causality in an accelerating universe places an absolute barrier between us and the thing we would need to observe. We cannot build a better telescope. We cannot wait longer. We cannot send a probe. The event horizon is not a technological challenge. It is a feature of the geometry of our situation. We are sealed inside our causal sphere, the way a message is sealed inside a bottle, except the bottle is surrounded not by ocean, but by a medium that is actively receding from the bottle at faster than the speed of any signal bottle could send. There is one more aspect of the cosmic event horizon that receives almost no attention in popular treatments and that changes the emotional character of the picture considerably once you absorb it. The event horizon is not fixed in place, it moves. Under the accelerating expansion of space driven by dark energy, the cosmic event horizon does not stay at 16.5 billion light-years from us indefinitely. Galaxies that are currently inside our event horizon, galaxies we can currently exchange signals with. Galaxies we currently have the ability to observe in real time are, at this very moment, drifting toward the event horizon. Eventually, each of them will cross it. Once a galaxy crosses outward through the event horizon, any signal it emits after the crossing will never reach us. The galaxy becomes causally severed from our future. The light already in transit from that galaxy at the moment of crossing light, emitted before the crossing continues to travel toward us. It will continue to arrive at our telescopes for an extended period after the crossing, slowly stretching to longer and longer wavelengths as the expansion redshifts it, growing dimmer and dimmer, asymptotically approaching but never quite reaching infinite redshift. In the far future, looking at such a galaxy through a sufficiently powerful telescope, we would see its last transmitted moments frozen in ever dimmer, ever redder light, a cosmological version of watching a clock slow to a standstill as it approaches the event horizon of a black hole. But nothing new from that galaxy, no signal sent after the moment of crossing will ever reach us. Right now, at this moment, somewhere in the sky, a galaxy is crossing our event horizon at a proper distance of approximately 16.5 billion light-years from where you are. A galaxy with its billions of stars, its interstellar clouds, its possible planets, its possible observers in whatever form observers might take, is at this instant moving permanently outside the volume of the universe we can interact with. The last light it will ever send us that we can receive is in transit right now, or will be soon. Everything after that moment is gone from our future. This is not a dramatic event from the perspective of anyone in that galaxy. The galaxy continues to exist. Its stars continue to burn. Nothing in the immediate physical environment of that galaxy changes at the moment it crosses our event horizon. The event horizon is not a physical structure the galaxy passes through. It is a boundary defined by our causal relationship to the galaxy, not by any property of the galaxy itself. From inside that galaxy, if there are observers capable of the relevant cosmology, our galaxy is what is crossing their event horizon, being removed from their future. The crossing is mutual, the isolation is mutual. The universe is, from the perspective of any local patch within it, slowly becoming more local, more isolated, more sealed inside its own causal sphere. Consider the long timescale of this process. The event horizon is currently at approximately 16.5 billion light-years. As cosmic time advances and dark energy continues to drive the acceleration of expansion, the event horizon slowly closes inward relative to the observable structures within our causal sphere. Galaxies at the edge of our current observational reach, the most distant galaxies we can detect, those near the particle horizon at 46.5 billion light-years, crossed our event horizon long ago, in cosmic terms. We see them, but we see them as they were in the early universe, and we will never receive any signal from them again corresponding to their current state. The galaxies we can currently exchange real-time signals with galaxies close enough that the light travel time is modest on cosmological scales, are not threatened by the event horizon on any timescale relevant to human civilization or even to the lifespan of the Sun. Our nearest large neighbor, the Andromeda Galaxy, at approximately 2.5 million light-years, is so far inside our event horizon that it is not in any danger of crossing outward for an incomprehensibly long time. But on the timescale of approximately 100 billion years, roughly 7 times the current age of the universe, the picture looks entirely different. By that point, the ongoing acceleration of cosmic expansion will have carried all galaxies beyond the local group, the gravitationally bound collection that includes the Milky Way, Andromeda, and several dozen smaller satellite galaxies across our event horizon. Every galaxy beyond the local group will have been causally severed from our future. The night sky, from the perspective of any observer existing in the Milky Way at that epoch, will contain no light from any external galaxy. The extragalactic universe, the hundreds of billions of galaxies visible to our current telescopes, will have gone dark from our perspective. Not because those galaxies will have died. They will still exist, still forming stars in many cases, still populated by whatever forms of complexity the universe allows. They will simply be beyond our event horizon, their light unable to reach us, their existence knowable to us in principle only from the records of observations made in our era, the cosmological equivalent of ancient documents describing a world that no longer has any physical connection to the present. What remains inside our event horizon at that distant epoch is the local group alone, the Milky Way and Andromeda, by then merged into a single large elliptical galaxy that astronomers sometimes informally call Milkomeda, surrounded by a scattering of dwarf satellite galaxies, an island in a darkness so complete that no instrument imaginable could detect the light of any other galactic structure. And outside, beyond the shrinking event horizon, in the volumes of space forever severed from that island, the engine of inflation continues to run. New bubbles nucleate. New patches of post-inflation space expand and cool. New cosmological histories begin. The process that produced our bubble does not care about the fate of the structures within our bubble. The process continues on its own terms, by its own dynamics, in volumes that our distant successors, if any exist, will have no way of knowing about and no way of reaching. The engine runs on. There is one place in the observational record where the separation between our bubble and the inflating background might not be complete. One anomaly, detected in the earliest and most comprehensive maps of the cosmic microwave background, that could in principle be a trace of contact between our bubble and the larger inflationary cosmos surrounding it. It sits in a particular region of the southern sky. It is colder than its surroundings by an amount that is, by the standards of the CMB, significant. It has been studied for over 20 years by teams using multiple independent techniques and multiple independent datasets. It remains unexplained to everyone's full satisfaction. It is called the cold spot. That is where we go next. The cosmic microwave background is, by almost any measure, the most uniform object in the observable universe. At a temperature of 2.72548 Kelvin, a number known with extraordinary precision from decades of satellite measurement, it fills the sky in every direction with thermal radiation so smooth, so consistent, so free of dramatic variation that describing it accurately requires language usually reserved for the most perfectly engineered objects human civilization has produced. The variations that exist across its surface are real, and they are scientifically indispensable. They are the seeds from which all large-scale structure in the universe grew. The primordial density fluctuations stretched to cosmic scales by inflation. But those variations are small, 1 part in 100,000, a whisper of temperature difference against a background of almost perfect stillness. Against that stillness, the cold spot stands out. It occupies a region of the southern sky in the constellation Eridanus, centered on galactic coordinates L equals 207.8 degrees, B equals negative 56.3 degrees. It is approximately 10 degrees across 20 times the angular diameter of the full moon, as seen from Earth, large enough that its extent across the sky is visible to careful statistical analysis without any ambiguity about whether the feature is real. At its edges, it is roughly 70 microkelvin colder than the average temperature of the surrounding CMB. At its deepest point, the coldest region near its center, the temperature dips to approximately 150 microkelvin below the mean. These numbers sound small. They are small in absolute terms, but in the context of the cosmic microwave background, where the total range of temperature variation across the entire sky spans only a few hundred microkelvin, a feature 150 microkelvin below average at its core is not small at all. It is, relative to the scale of ordinary CMB fluctuations, a substantial anomaly. The probability of finding a cold region this extreme, this cold, this large, this statistically coherent arising by chance in a universe whose primordial fluctuations follow the Gaussian random distribution predicted by standard inflation is approximately 1 in 1,000. Not impossible, not physically ruled out, but rare enough by the standards of a field accustomed to treating 5 sigma results as discoveries that it demands an explanation. The cold spot was first formally identified and characterized in 2004 by a team led by Pablo Vielva at the Instituto de Física de Cantabria in Spain in a paper published in the Astrophysical Journal, volume 609, page 22. Vielva and collaborators applied a mathematical technique called the spherical Mexican hat wavelet, transformed to the WMAP first-year data, a method designed to isolate features at specific angular scales, and found a statistically significant non-Gaussian signal in the southern sky. The signal corresponded to the cold region in Eridanus. Since 2004, the cold spot has been analyzed by more groups using more techniques than almost any other single feature of the CMB. It has been examined with WMAP data across 7 years of observations. It has been examined with Planck data across multiple data releases through 2018. Its statistical significance has been debated, refined, and re-examined. Its angular profile has been measured in detail. Its polarization properties have been studied. The basic conclusion has remained stable across 20 years of increasingly precise analysis. There is a cold region in Eridanus. It is statistically anomalous, and the standard inflationary model inflation producing a Gaussian random field of primordial fluctuations does not predict it. What does predict it, or might predict it, is the question that has generated 2 decades of productive disagreement. The first and more conventional interpretation invokes a structure in the foreground universe, in the matter distribution between us and the surface of last scattering, rather than anything in the primordial CMB itself. In 2015, a team led by Istvan Zapudi at the University of Hawaii's Institute for Astronomy published a paper in Monthly Notices of the Royal Astronomical Society, volume 450, page 288, reporting the identification of a large, underdense region of space in the direction of the cold spot at a redshift of approximately 0.15. This structure, called the Eridanus supervoid, is a region where the density of galaxies and dark matter is significantly below the cosmic average. It spans approximately 1.8 billion light-years in extent and represents one of the largest known underdense structures in the observable universe. The physical mechanism connecting the supervoid to the cold spot is called the integrated Sachs-Wolf effect. As CMB photons travel through the universe on their way to our detectors, they pass through regions of varying gravitational potential regions where the concentration of matter creates gravitational wells that photons must climb out of. In a universe dominated by matter alone, a photon that falls into a gravitational well gains energy on the way in and loses the same energy on the way out, ending at the same energy it began with. The gravitational potential well does not affect the photon's final temperature. But in a universe with dark energy in the universe, we actually inhabit the gravitational potential wells are not static. As the universe's expansion accelerates under the influence of dark energy, the large-scale structure of matter evolves, and the gravitational potential wells associated with that structure gradually change their depth. A photon passing through an underdense region, a void where the gravitational potential is shallower than average, finds that the potential has changed slightly during the transit. The photon enters the void, traverses it, and emerges at a slightly lower energy than it carried when it entered. The passage through the evolving void costs the photon a small amount of energy. It emerges slightly cooler. This is the integrated Sachs-Wolf effect in voids. And the Eridanus supervoid, given its size and its location along the line of sight to the CMB cold spot, should produce a cooling effect on the CMB photons passing through it. The question is whether it produces enough cooling to account for the observed cold spot entirely. The honest answer, based on the analyses published through 2025, is that it does not, or at least not quite. The integrated Sachs-Wolf contribution from the Eridanus supervoid accounts for a significant portion of the cold spot's temperature deficit. The supervoid is real, the effect is real, the connection between them is physically well motivated, but when theorists calculate the expected temperature decrement from the supervoid, using the standard cosmological model and compare it to the observed cold spot, there remains a residual, a portion of the cold spot's anomaly, that the supervoid alone does not fully explain. The residual is not enormous. It is statistically small enough that many cosmologists treat the supervoid as a sufficient explanation and attribute the remainder to statistical fluctuation, the universe being slightly colder in that direction than average, as it must be somewhere by the nature of random processes. But the residual exists, and it is the residual that keeps alive the second interpretation. The second interpretation connects the cold spot directly to the eternal inflation picture this video has been developing. In a series of papers published between 2006 and 2008, a group of cosmologists including Stephen Feeney, Matthew Johnson, Daniel Mortlock, and Hiranya Peris developed a theoretical framework for predicting what a collision between our bubble universe and another bubble nucleating in the inflating background would look like in the cosmic microwave background. Their work built on earlier theoretical foundations laid by researchers including Anthony Aguirre and Matthew Johnson, who had analyzed the dynamics of bubble collisions in an eternally inflating spacetime. The prediction that emerged from this framework was specific. A collision between our bubble and another bubble in the inflationary background would deposit energy asymmetrically into the post-collision region of our universe, creating a localized pattern of temperature variation in the CMB. The pattern would be circular, a disc-shaped region, because the geometry of a bubble collision in an inflating background has a natural rotational symmetry around the axis, connecting the centers of the two colliding bubbles. The disk would be cold or hot, depending on the details of the collision geometry and the relative properties of the two bubbles involved. The prediction was made before the cold spot had been fully characterized in statistical detail. It was not tuned to match the cold spot. It was a theoretical derivation of what bubble collision signatures should look like in general, based on the dynamics of bubble collisions in de Sitter space. When the prediction was compared to the observed cold spot in Eridanus, the qualitative match was striking. A cold, circular, disc-shaped region of the CMB, statistically anomalous, in a Gaussian random field. This is precisely the description that the bubble collision framework predicted should exist if our bubble had collided with another bubble at some point in its early history. The angular scale, the rough temperature profile, the circular geometry, all of these features are consistent with what a bubble collision should produce. The match is not perfect. There are aspects of the cold spot's detailed structure that do not fit the simplest bubble collision models cleanly. The polarization properties of the cold spot, in particular, have not shown the distinctive signatures that some bubble collision scenarios predict, and the conventional supervoid explanation accounts for the bulk of the temperature deficit without invoking any exotic mechanism. But the qualitative consistency between the bubble collision prediction and the observed cold spot is genuine enough that the interpretation has remained a live possibility in the theoretical literature for nearly 2 decades. The systematic search for bubble collision signatures, not just at the location of the cold spot, but across the entire CMB sky, has been pursued with increasing rigor since the Feeney-Johnson-Mortlock-Peris papers appeared. In 2011, The same team published a systematic search in Physical Review Letters, Volume 107, Article 071301, applying a Bayesian template-fitting procedure to the full WMAP 7-year sky maps. The procedure tested for the specific disk-shaped temperature patterns predicted by bubble collision models at every location on the sky, at every angular scale within the relevant range, and with every predicted amplitude. The result was a null detection. No bubble collision signature, statistically significant by the standards the team defined in advance, appeared in the WMAP data. Subsequent analyses using the Planck data through 2018 and extending through the most recent data releases available as of 2024 have continued the search with the same outcome. The CMB sky, examined with the most sensitive instruments we have and the most carefully designed statistical tests the community has developed, does not show unambiguous evidence of bubble collisions. The cold spot in Eridanus is the closest the search has come to a positive detection, and even the cold spot, as we have seen, has a plausible conventional explanation that requires no exotic physics. This is the empirical situation with honesty applied to it. The cold spot is real, its statistical anomaly is real, the Eridanus supervoid is real, and contributes to the cold spot's temperature deficit. The residual after the supervoid contribution is subtracted is small but present. The bubble collision hypothesis matches the cold spot's qualitative character. The systematic searches for bubble collision signatures across the full sky have returned null results. The cold spot is not proof of eternal inflation. It is not proof of a bubble collision. It is, at best, a feature that is more consistent with the bubble collision hypothesis than most regions of the CMB sky are, in a context where the conventional explanation accounts for most, but not all of the observed signal. Science at the edge of what can be tested looks like this: not clean confirmation, not clean refutation, data that is consistent with multiple interpretations, where the exotic interpretation cannot be ruled out, and the conventional interpretation cannot fully account for every detail. Researchers continuing to look, continuing to refine their analyses, continuing to develop better predictions and better tests. A question that has been open for 20 years and may remain open indefinitely. The cold spot is the most discussed potential observational fingerprint of eternal inflation, but it is worth noting briefly that the search for such fingerprints extends beyond the CMB. Signatures of bubble collisions could in principle appear in the large-scale distribution of matter, in the way galaxies are arranged across the sky on the largest observable scales. They could appear in the statistical properties of the CMB polarization field, which the next generation of CMB experiments, including the Simons Observatory in Chile and the planned CMB S4 experiment, will measure with unprecedented sensitivity. They could appear as anomalies in the angular correlations of the CMB temperature field at scales larger than those best measured by Planck. Some of these anomalies exist. The CMB has long been known to contain a handful of features at the largest angular scales, features sometimes collectively called the CMB anomalies that sit in mild tension with the standard inflationary prediction of a perfectly Gaussian random field. The quadrupole and octupole moments of the CMB temperature distribution show an unexpected alignment with the ecliptic plane. The power spectrum at the very largest angular scales is slightly lower than the standard model predicts. These anomalies have been studied intensively, and no consensus explanation has emerged. None of them is individually compelling enough to constitute evidence of bubble collisions or eternal inflation. Collectively, they represent a mild but persistent whisper from the data that something at the largest scales might not fit the standard picture perfectly. Whether that whisper is signal or noise, whether it is telling us something about the physics operating beyond our event horizon, or simply reflecting the inevitable statistical scatter in measurements of a universe, of which we can to observe only one realization, is not known. The answer may never be known, because the event horizon that seals us from the inflating background also seals us from the definitive test. We have strong theoretical reasons to believe the engine is still running. We have one contested potential fingerprint in the southern sky. We have systematic searches that have returned null results. And we have a permanent causal barrier that prevents us from resolving the question by direct observation. This is the honest position. It is uncomfortable by the standards of a field accustomed to resolving its major questions eventually. Most questions in physics yield to better instruments, longer observations, cleverer experiments. The eternal inflation question may not. It may sit permanently at the boundary of the testable implied by a well-confirmed theory, consistent with what we observe, but forever beyond the reach of a definitive empirical verdict. Some physicists find this intolerable. They argue that a prediction permanently beyond empirical reach is not a scientific prediction at all, that science without testability is philosophy, and that the inflation community, by accepting eternal inflation as a consequence of confirmed theory, has crossed a line that should not be crossed. That argument has a name, and the people who made it publicly in its strongest form are serious physicists who deserve serious engagement. That is where we go next, the critique that forced inflation to defend itself. In February of 2017, Scientific American published an article that caused more sustained discussion within the cosmological community than almost anything else that appeared in a popular science venue that decade. The article was titled, "Pop Goes the Universe." Its authors were three physicists, Anna Ijas, Paul Steinhardt, and Abraham Loeb. Its tone was measured, its language was precise, and its argument was, in the considered judgment of a significant portion of the working cosmology community, a direct challenge to the theoretical foundations of the field's leading framework for understanding the earliest moments of the universe. The three authors were not outsiders. They were not skeptics attacking a theory they had never worked with from a position of unfamiliarity. Paul Steinhardt had been one of the original architects of new inflation in the early 1980s. He had worked alongside Linde and others in developing the slow-roll framework that became the standard version of the theory. He had spent years building the very edifice he was now examining with critical eyes. Abraham Loeb was the chair of Harvard's astronomy department, one of the most cited astrophysicists of his generation, with a research portfolio spanning galactic dynamics, black hole physics, and cosmology. Anna Ijas was a younger theorist with expertise in the mathematical structure of inflationary models and their relationship to fundamental physics. When these three physicists published a critique of inflation in the most widely read popular science magazine in the United States, the community paid attention. Their argument operated on two levels, each reinforcing the other. The first level concerned the falsifiability of the inflationary framework in general. Ijas, Steinhardt, and Loeb argued that the space of inflationary models, the collection of distinct theoretical versions of inflation that can be constructed by choosing different shapes for the inflaton potential, is so vast and so flexible that virtually any observational result can be accommodated within. To it, measure the scalar spectral index and find it is 0.96. There is an inflation model that predicts 0.96. Find it is 0.94. There is an inflation model that predicts 0.94. Measure the ratio of gravitational wave amplitude to density fluctuation amplitude and find it is large, small. There are inflation models predicting both. Detect a departure from Gaussian statistics in the CMB. There are non-standard inflation models that produce non-Gaussianity. The flexibility is not an accident. It is a consequence of the theoretical structure. The inflaton potential is a free function, a mathematical object that can be given almost any shape consistent with some very general smoothness conditions. Different shapes produce different inflationary predictions. Because the space of possible shapes is effectively unlimited, the space of possible predictions is effectively unlimited too. A framework that can accommodate any observation, they argued, is not a scientific theory in the sense that physics has historically demanded. A theory that cannot be falsified, that has no prediction it is committed to, no result that would force its abandonment, is not constraining our picture of nature in the way science is supposed to constrain it. The Planck satellite's measurement of the scalar spectral index at 0.9649 had been celebrated as a confirmation of inflation. But Ijas, Steinhardt, And Lowe pointed out that the Planck result actually disfavored many of the simplest and previously most popular inflation models, the large field models with power law potentials that had dominated the theoretical literature before the measurement. The fact that inflation as a framework survived the Planck result was not, in their view, evidence that inflation was confirmed. It was evidence that inflation was flexible enough to accommodate whatever the data said, which is a very different thing. This argument was pointed. It was also, in the view of many physicists, overstated. Every successful physical theory contains adjustable parameters and free functions that are constrained by measurement rather than fixed by the theory itself. The standard model of particle physics has 19 free parameters. General relativity applied to cosmology has several. The accusation that a theory is untestable because it contains adjustable parameters would, if applied consistently, undermine most of theoretical physics. The relevant question is not whether a theory has free parameters, but whether measurements constrain those parameters in ways that make specific predictions, and on this criterion, the inflation community would argue, inflation has done exactly that. The scalar spectral index is now constrained to within a fraction of a percent. The tensor-to-scalar ratio has an upper bound that rules out large classes of models. The amplitude of primordial non-Gaussianity is bounded tightly enough to exclude many multi-field inflation scenarios. But the first level of the Ijs-Steinhardt-Loeb argument, however contested, served primarily as a setup for the second level. The second level was the argument that matters most for this video. The second argument targeted the eternal inflation extension specifically, and it was, in its own terms, considerably more difficult to deflect. Eternal inflation, they argued, does not merely make the inflationary framework flexible, it makes it infinitely flexible in a way that entirely removes the theory from the domain of empirical science. If eternal inflation is correct, then every possible outcome that is consistent with the laws of physics occurs somewhere in the infinite ensemble of bubble universes. Every possible value of every cosmological observable, every possible structure of large-scale matter distribution, every possible temperature pattern in every possible bubble universe's cosmic microwave background. All of it happens, infinitely many times, somewhere in the inflating background. In such a framework, any observation we make is automatically consistent with the theory. Whatever we measure, whatever spectral index, whatever tensor-to-scalar ratio, whatever large-scale structure, whatever CMB temperature pattern that measurement exists in the predicted ensemble, the theory predicted it. The theory also predicted every other possible measurement. A theory that predicts everything predicts nothing. A theory that cannot be falsified by any conceivable observation is not, in the strict epistemological sense that Karl Popper articulated and that physics has generally accepted, a scientific theory at all. They gave this failure mode a name. They called it the multi-mess, the situation in which the multiverse predicted by eternal inflation, rather than being an extension of science into previously unreachable domains, represented a collapse of the scientific enterprise into a framework where empirical testing became meaningless. The multi-mess argument is the sharpest version of the falsifiability critique of eternal inflation. It does not merely say the theory is hard to test. It says the theory predicts every possible result, and a theory that predicts every possible result is not distinguishable in any operationally meaningful sense from a theory that predicts nothing. This is a genuine philosophical challenge. It is not easily dismissed by pointing to the precision of inflation's tested predictions, because those predictions, the spectral index, the smoothness of the CMB, the absence of monopoles, are predictions of the single bubble inflationary phase within our observable patch, not predictions of the eternal inflation extension. The eternal inflation extension is an additional claim layered on top of the tested single bubble predictions, and it is the extension that the multi-mess argument targets. One can in principle accept all of inflation's tested predictions while rejecting eternal inflation as an untestable and therefore non-scientific appendage. The cosmological community's response came the following month. In March of 2017, a letter, published in Scientific American, was signed by 33 physicists whose collective expertise in theoretical cosmology, particle physics, and gravitational theory represented a substantial fraction of the field's senior leadership. The signatories included Alan Guth, the originator of inflation, André Linde, the architect of new inflation and chaotic inflation, and the discoverer of eternal inflation, Stephen Hawking, whose contributions to cosmology and quantum gravity required no introduction, Steven Weinberg, a Nobel laureate whose theoretical work spanned the Standard Model and cosmological constant problem, Lawrence Krauss, whose public engagement with cosmology had made him one of the most recognized physics communicators of his generation, Eva Silverstein, whose research on string-theoretic approaches to inflation represented the frontier of the theoretical program, Sean Carroll, a cosmologist whose work on the arrow of time and the foundations of quantum mechanics had shaped philosophical discussions of cosmology for years. 33 physicists, representing decades of collective work on the theory under attack, defending it in the pages of the same magazine that had published the attack. Their response addressed the falsifiability argument at both levels. On the first level, the claim that the inflationary framework is too flexible to be testable, they argued that the existence of free parameters does not imply unscientific status. The relevant criterion is whether measurements constrain those parameters and whether the resulting constrained theory makes predictions that could, in principle, be refuted. Inflation, they argued, clearly satisfies this criterion. The Planck constraints on the spectral index, the tensor-to-scalar ratio, and the amplitude of non-Gaussianity represent genuine theoretical commitments that genuinely constrain the class of inflation models consistent with nature. The framework is not infinitely flexible in practice, even if the space of possible models is large. On the second level, the multi-mess argument against eternal inflation specifically, they made a more subtle and more philosophically interesting response. They argued that eternal inflation is not a separate theoretical claim that can be accepted or rejected independently of the single-bubble inflationary predictions. It is a consequence, a deduction that falls out of the dynamics of inflation when those dynamics are applied honestly and completely. The same equations that produce the single-bubble predictions, when allowed to run without artificial termination, produce the eternal inflation result. If you trust the equations enough to believe they're single-bubble predictions and the Planck data says you should, then you must follow those equations wherever they lead, and they lead to eternal inflation. The argument the 33 physicists were making has a name in the philosophy of science. It is called inference to the best explanation, or sometimes abductive reasoning. The principle is that when a theory provides the best available explanation for a set of observations, we are justified in extending our confidence in that theory to its untested predictions as well as its tested ones. We trust the tested predictions because the theory earned that trust through empirical confirmation. We extend that trust to the untested predictions, not because we have tested them, we may never be able to test them, but because they are derived from the same theoretical framework that earned our trust elsewhere. This is not a new or exotic principle. It underlies a great deal of physics. We accept the existence of the interior of black holes not because any observer has ever returned from inside one with a first-hand report, but because the theory of general relativity, which is confirmed to extraordinary precision in every domain we can test, makes specific predictions about what exists inside black holes. We accept those predictions because we trust the theory. The interior of a black hole is, in a certain sense, permanently beyond empirical reach. No information from inside a black hole's event horizon can ever reach an external observer. Yet no physicist considers the interior of black holes to be outside the domain of science. Eternal inflation, the 33 physicists argued, occupies a structurally similar position. It is a region of physical reality that is beyond our direct observational reach, predicted by a theory that is confirmed in every aspect we can test. The appropriate response to this situation is not to declare the prediction unscientific. The appropriate response is to accept the prediction as our best current understanding of what lies beyond our observational horizon, while remaining open to refining or revising that understanding if better theory or unexpected observations demand it. The exchange did not resolve the underlying disagreement. Ejas, Steinhardt, and Loeb were not persuaded by the rebuttal. Their subsequent publications have continued to develop alternative cosmological frameworks, most notably bouncing cosmologies, in which the universe contracts before expanding, avoiding the singular Big Bang and the inflationary phase entirely. The inflation community has continued to develop and refine inflationary theory, accumulating increasingly precise measurements that continue to be consistent with the inflationary predictions. As of 2026, the dispute is not settled. It is, in the technical literature, somewhat quieter than it was in 2017. The most dramatic public exchange has subsided, and both sides have returned to doing their research. But the questions it raised about the boundaries of scientific legitimacy, about what it means for a theory to make a prediction, about whether untestable consequences of testable theories deserve epistemic respect, these questions remain open. They are live issues in the philosophy of science and in the self-understanding of the cosmological community. What the exchange reveals, for the purposes of this video, is something important and perhaps surprising. Eternal inflation is not a fringe extension of inflation that the mainstream community quietly distances itself from when pressed. It is a core feature of the theory that 33 senior physicists, including the theory's original creators, defended publicly in the most prominent popular science venue available, when they perceived it to be under attack. The defense was not qualified. The signatories did not say, "We are not sure about eternal inflation, but we are confident about the rest of inflation." They said eternal inflation follows from the dynamics of inflation, that those dynamics are well confirmed, and that the prediction therefore deserves the same epistemic status as the rest of the theory's predictions. They were saying, "This is what the theory says. We stand behind it." The implication is stark. The mainstream community of working cosmologists, not all of them, not without dissent, but the majority represented by the 33 signatories and by the broader working consensus of the field, treats the inflating background, the ongoing production of new bubble universes, the eternal continuation of the process that produced our local patch, as the default expectation for what exists beyond our event horizon, not as a speculation, not as a possibility, as the prediction of their theory, and their theory, in every aspect it can be tested, has been confirmed. This is the position from which the next chapters of this video operate. Eternal inflation is the prediction of a confirmed theory. The prediction cannot be directly tested from inside our bubble. The prediction is nonetheless taken seriously by the community that built and tested the theory. The math kept producing it. The community accepted it. The defense was public and unambiguous. What remains is to understand what the prediction means, not just physically, but in terms of what it implies about the nature of our existence within the universe it describes. Specifically, what does a spatially infinite universe, even before invoking the eternal inflation extension, imply about the uniqueness of your experience of this moment? What does the arithmetic of infinite space and finite physical configurations actually tell you about how many other versions of you currently exist? The answer is uncomfortable. The calculation is not speculative. It requires only the flatness measurement and the cosmological principle, the two most basic inputs of standard modern cosmology. That is where we go next. The other versions of you that the mathematics cannot avoid producing. There is a calculation that follows directly from accepting the simplest reading of the Planck flatness measurement. No eternal inflation required, no quantum branching, no exotic theoretical extension of any kind that produces one of the most psychologically destabilizing results in the history of cosmological reasoning. The calculation was articulated with full mathematical precision by the physicist Max Tegmark in a 2003 article in Scientific American, and developed at considerably greater length in his 2014 book Our Mathematical Universe. But the result itself was not Tegmark's discovery. Working cosmologists had been aware of the implication for years before Tegmark named it and made it the centerpiece of a systematic classification of multiverse types. What Tegmark contributed was the explicit arithmetic, the willingness to state the conclusion without softening it, and a taxonomy that allowed the result to be discussed precisely rather than vaguely. The result is this. In a spatially flat, spatially infinite universe governed by the same physical laws everywhere, the specific arrangement of matter and energy within any finite region of space, any region with a finite volume, containing a finite number of particles must eventually repeat. Not might repeat, must. The repetition is not a possibility that can be avoided with sufficiently exotic initial conditions or sufficiently unusual physics. It is a mathematical certainty that follows from the structure of infinite space and finite physical configurations. It is, at its core, an application of a principle so elementary that it appears in undergraduate combinatorics courses as an introductory exercise. That principle is the pigeonhole principle. If you have more pigeons than pigeonholes, at least two pigeons must share a hole. If the number of distinct possible configurations of matter within a finite volume is finite, and the number of such volumes in the universe is infinite, then the configurations must repeat. There are not enough distinct arrangements to fill an infinite universe without duplication. Both inputs to this argument, the finite number of configurations and the infinite number of volumes, follow from assumptions that the working cosmological community treats as its default operating position. Let us examine each in turn. The number of distinct possible arrangements of matter within a region the size of our observable universe within a sphere approximately 46.5 billion light-years in radius is finite. This is not immediately obvious because the number is astronomically large, and large numbers have a way of feeling infinite even when they are not. But the finiteness follows from the quantization of physical states at the Planck scale. In quantum mechanics, the state of a physical system is not a continuous variable that can take on any value from an uncountable continuum. Physical states are quantized. Position is quantized at the Planck length, approximately 1.6 times 10 to the power of negative 35 meters. Momentum is quantized in units determined by the Planck scale and the size of the region being considered. The total number of distinct quantum states available to a system of particles within a bounded region of space is therefore finite enormous, beyond any practical comprehension, but finite in the strict mathematical sense. The number of particles in our observable universe is estimated at approximately 10 to the power of 80 protons, neutrons, and electrons, the constituents of ordinary matter, with dark matter and neutrinos adding somewhat to the total, depending on counting conventions. The number of possible arrangements of these particles in the available quantum states within the observable volume is a number that cannot be written in standard scientific notation without resorting to towers of exponents. It is something like 10 raised to the power of 10 raised to the power of 120, a number whose magnitude is so far beyond ordinary intuition that comparing it to the number of atoms in the observable universe is like comparing the distance to the moon to the width of a proton. But it is finite. It is a specific number. It has a definite value, however incomprehensible that value is to human intuition. Now, consider the second input. If the universe is spatially flat, and the cosmological principle holds, if the same physical laws operate everywhere, and the geometry of space extends without boundary, then the universe contains an infinite number of regions, the size of our observable universe. Not a large number, not a number too large to write down, an actually infinite number. For every finite count, you can name a trillion, a Googleplex. The infinite flat universe contains more Hubble volume-sized regions than that count. Apply the pigeonhole principle. A finite number of possible configurations, however large, distributed across an infinite number of volumes. The configurations must repeat. Every configuration that exists in our observable volume must exist in infinitely many other volumes, scattered across the infinite extent of space, including the configuration that is U. Tegmark made this concrete by calculating a specific number, the expected distance to the nearest region of space whose configuration of matter and energy matches our observable universe, precisely matches it down to the position of every particle, the state of every quantum field, the arrangement of every atom in every molecule in every cell of every organism on every planet in the observable volume. The number he calculated is approximately 10 to the power of 10 to the power of 29 meters. Let us spend a moment with this number, because it resists every ordinary attempt at comprehension and deserves the effort. The observable universe is approximately 8.8 times 10 to the power of 26 meters in diameter. This is the scale against which cosmological distances are usually measured, the largest scale accessible to human observation, the scale of the most distant light that has ever reached our detectors. The distance to the nearest identical Hubble volume is 10 to the power of 10 to the power of 29 meters. This is not 10 to the 29th power that would be a comprehensible, if enormous distance, roughly 10 billion times the diameter of the observable universe. It is 10 to the power of a number that is itself 10 to the 29th power. It is a tower of exponents whose height is itself an incomprehensible number. There is no unit system, no analogy, no visualization technique available to human cognition that can make this number feel like a distance rather than an abstraction. And yet it is finite. That is the point. The distance is not infinite. It is not unreachable in principle, only in practice, and in practice so thoroughly unreachable that the distinction between very far and infinitely far collapses for any purpose other than the pure mathematical one. But mathematically, the distinction matters. The nearest identical copy of our observable universe is at a finite distance. It exists. The mathematics of a flat infinite universe with uniform physics places it there, and the mathematics does not offer the option of removing it. There is a version of this result that sits closer to you personally than the nearest identical Hubble volume, considerably closer, though still at a distance that makes the observable universe seem intimate by comparison. The nearest identical Hubble volume is identical in every detail, every particle, every field configuration, every quantum state, every cosmological history, extending back to the earliest moments after the Big Bang. To produce such a perfect match requires reproducing not just your current physical state, but the entire causal history that produced it, the specific sequence of events across 13.8 billion years that resulted in this particular arrangement of matter at this particular moment. But you do not need a perfect historical match to produce a brain indistinguishable from yours in this moment. You need only match the physical state of your brain, the specific configuration of neurons, the specific pattern of electrical activity, the specific chemical concentrations at every synapse at this instant, regardless of how that state came to be. The causal history that produced the state matters for how the state got there. It does not matter for what the state is right now. The nearest region whose matter configuration matches the state of your brain and therefore produces a conscious experience indistinguishable from yours in this moment is much closer than the nearest full Hubble volume match. Tegmark estimated this distance in his 2014 book at approximately 10 to the power of 10 to the power of 16 meters, still a number that no human intuition can genuinely process. Still a distance that makes intergalactic travel seem trivial by comparison, but finite, definite, real, within the mathematics of a flat infinite universe. And the number of such regions, the number of locations in the infinite universe where a brain in exactly your current state exists is not finite, it is infinite. There are infinitely many instances of the physical configuration that constitutes your experience of this moment, distributed across the infinite expanse of flat space, each one isolated within its own observable patch, each one experiencing what feels, from the inside, like the singular and unrepeatable character of conscious experience, each one, in the ordinary and unavoidable human sense, believing itself to be the only one. Sit with this for a moment before we continue. The argument for the existence of these copies does not depend on speculation about the nature of consciousness. It does not depend on any particular theory of mind or any particular view of what makes an experience subjective. It depends only on the physical state of the brain, the arrangement of matter and energy in the neurons, and their connections being a specific configuration of particles in a finite volume of space. If that configuration exists in our observable volume, and the universe is flat and infinite and governed by the same physics everywhere, then the configuration exists in infinitely many other volumes. The copies are real, in the same sense that the particles constituting them are real. The copies are not hypothetical. They are not possible, they are actual. Most people, when they first encounter this argument, reach for one of several objections. The first objection is that the cosmological principle might not hold, that the universe might not be uniform on large scales, that the physics in distant regions might be different from the physics here, in ways that change the calculation. This is a legitimate scientific possibility. The cosmological principle is an assumption, not a proven fact. If it fails, the argument for the level 1 multiverse fails with it. But the cosmological principle is supported by every large-scale structure survey we have conducted. The universe, on the scales we can probe, is remarkably uniform, and the inflationary theory that explains the flatness measurement also predicts the uniformity inflation smooths pre-existing inhomogeneities and produces a universe that is, on the largest scales, extraordinarily homogeneous. Rejecting the cosmological principle means rejecting one of the most well-supported assumptions in modern cosmology. The second objection is that the flatness measurement might be wrong, that the universe might be closed and finite after all, even if the curvature is too small to detect. We examined this in the chapter on the Planck measurement. A closed universe is consistent with the data within the measurement uncertainties, but a closed universe, consistent with the Planck measurement, must have a radius at least 250 times larger than the observable patch, roughly 11,500 billion light-years. Such a universe is finite, and the Tegmark level 1 argument does not apply to it in exactly the same form. The copies might not exist in a finite universe, depending on how large the universe is relative to the number of distinct configurations. Whether they exist depends on the specific size of the closed universe, which we cannot determine from inside our observable patch. The third objection is that quantum mechanics might change the picture, that the quantization of physical states might not work in the way the argument assumes, or that quantum entanglement across large distances might impose constraints on which configurations can coexist in different regions of an infinite universe. This objection is more technically involved and more difficult to evaluate. Quantum field theory does impose constraints on physical states that a purely classical combinatorial argument might miss. But the broad structure of the Tegmark argument that a flat infinite universe with finite possible configurations per finite volume must produce repetitions survives standard quantum mechanical reasoning. The details of the counting change, but the qualitative conclusion remains. The reason the level 1 multiverse, the copies implied by a flat infinite universe, deserves careful attention in a video about eternal inflation is precisely that it requires no eternal inflation. It requires no bubble collisions. It requires no quantum branching or many worlds interpretation. It requires only the two assumptions that underlie the standard working model of cosmology that every introductory cosmology course teaches. The universe is flat, and the cosmological principle holds. If you have accepted those two assumptions, and the cosmological community's working consensus is that you should, given the observational evidence, then you have already accepted the existence of infinitely many copies of your current physical state distributed across the infinite expanse of space. The exotic conclusion follows from the conventional starting point. No additional theoretical moves are required. Eternal inflation adds a layer to this picture, but the additional layer is in some sense a refinement rather than a revolution. The eternal inflation extension predicts that the infinite flat universe containing level Y copies is not the whole story, that there are also other bubble universes outside our event horizon, possibly with different fundamental constants and different physical laws, each of those bubbles also infinite and flat, and containing their own level I copies. The total structure becomes a hierarchy of infinities. Infinite copies within each bubble, an infinite number of bubbles, each bubble containing an infinite internal ensemble. The Tegmark classification calls this the level 2 multiverse. But the level 2 picture, however mind-expanding, is in its basic character simply more of what the level I picture already implies. The level I picture is already sufficient to establish the fundamental point. You are not unique within the universe. The universe under the assumptions the working community treats as its operating default, contains an infinite number of physical configurations identical to yours. The experience you are having right now, in this moment, as you process these words, is being had simultaneously by an infinite number of other physical systems at various distances across the infinite expanse of flat space. The experience feels singular from the inside. It is not singular from the outside, if outside means the vantage point of the mathematics describing the full extent of the universe. There is a particular quality to sitting with this conclusion that is different from sitting with other large number results in cosmology. The number of stars in the observable universe, approximately 10 to the power of 24, is large enough to be functionally incomprehensible, but it does not disturb the basic structure of personal experience. It simply says, there are many stars. The level I multiverse result is different. It says that your specific configuration of matter, the specific physical state that constitutes whatever it is you are in this moment, is not rare, it is not unique. It is replicated infinitely many times across the universe that standard cosmology describes. The uniqueness you feel is real at the scale of your causal sphere. Within the observable universe, within the patch of space, you can in principle exchange signals with. Your specific configuration is almost certainly unique. The probability of an identical configuration arising by chance within the observable volume is vanishingly small. The uniqueness is local. At the scale of the full infinite universe, the uniqueness dissolves into an infinite ensemble of identical instances. What to do with this, how to carry it, how to integrate it into an ordinary human experience of being a particular person in a particular place at a particular moment is not a question science answers. Science produces the result. The living with it is something else. What the mathematics does not allow you to do is pretend the result is not there. The math kept producing it. It produces it from the cleanest reading of the Planck measurement and the most standard assumption of the cosmological principle. Before eternal inflation enters the picture, before any speculative extension of any kind, from the data alone, applied honestly and completely. In the next chapter, we will name the engine that sits beneath all of this, the engine that produced our local patch, that continues producing new patches beyond our event horizon, that makes the universe not just infinite in the geometric sense, but infinite in the ongoing, active, present tense sense of a process that is still running right now, while you hold these words in your mind. The engine is not a metaphor. It has a specific physical description. It has specific equations. It has a specific mechanism. And once we have named it precisely, the phrase we planted at the beginning of this video, the engine that made us is still running, will carry a weight it could not have carried before we built the structure beneath it. That is where we go next. We have now assembled enough structure to do something we could not have done at the beginning of this video. We can name the engine precisely, not gesture toward it, not invoke it as a poetic device. Name it, describe its physical mechanism, state its governing equations in plain language, explain why it has no off switch, and make clear what it means for that engine to be running right now, in this moment, in volumes of space just beyond the boundary of what any instrument we could ever build would ever show us. The engine is the inflaton field. More precisely, it is the inflaton field in the regions of the universe where the field value remains high, where the potential energy stored in the field has not yet been converted into the matter and radiation that constitute a post-inflation bubble like ours. In those regions, the field sits at a high point on its potential energy landscape. In those regions, the energy density of space is dominated by the potential energy of the field rather than by matter or radiation. And in those regions, Einstein's equations of general relativity produce a specific and unambiguous result. Space expands exponentially, not linearly, not as a power law, exponentially, doubling on a fixed timescale determined by the value of the field and the shape of the potential. In the simplest models of chaotic inflation, the models Linde developed in 1983 that produce eternal inflation, most naturally, the doubling timescale is approximately 10 to the power of negative 34 seconds, 1/10,000th of a trillionth of a trillionth of a trillionth of a second. a span of time so brief that no physical process accessible to human observation operates on anything close to its scale. Let us be precise about what doubling on this timescale means for the volume of the inflating background. Start with a single cubic meter of inflating space somewhere in the region beyond our event horizon, a volume the size of a large cardboard box, containing nothing but the inflaton field at a high potential value and the exponentially expanding geometry it drives. After 10 to the power of negative 34 seconds, that cubic meter has become 2 cubic meters. After another 10 to the power of negative 34 seconds, it is 4. After 10 doublings, a total elapsed time of 10 to the power of negative 33 seconds, it is roughly 1,000 cubic meters. After 100 doublings, 10 to the power of negative 32 seconds, it is 10 to the power of 30 cubic meters, larger than the observable universe. After 10,000 doublings, 10 to the power of negative 30 seconds, still less than a billionth of a second, it is a volume. These numbers do not correspond to anything in ordinary experience. They are not large in the way that the number of stars in the observable universe is large, a number that, however incomprehensible in practical terms, can at least be written down in a few digits of scientific notation. The volumes produced by exponential inflation on these timescales require notational systems that themselves require explanation. They are large in the way that nothing in the physical universe accessible to us is large. And this is happening right now, not in the past, not in the early universe, in the fraction of the first second after the Big Bang, as the standard telling of the inflation story suggests. Now, at this moment, in the regions of the universe that lie beyond our cosmic event horizon, the inflaton field continues to sit at high potential values in the regions where the quantum fluctuations have sustained it there. The exponential doubling continues. The volume of inflating space grows by factors that make the entire observable universe look like a rounding error. There is a conceptual subtlety in this picture that is easy to misunderstand, and getting it right changes how the engine feels. When we say the volume of inflating space is growing, we do not mean that the inflating region is expanding into some pre-existing space that surrounds it, the way a balloon expands into the air of a room, or a city expands into the surrounding countryside. There is no surrounding space. There is no external arena into which the inflating region grows. The growth is intrinsic to the geometry of the inflating region itself. What is happening is this: the metric of space, the mathematical structure that determines distances between points, is changing within the inflating region. The distance between any 2 points in the inflating background increases exponentially with time. 2 points that were 1 meter apart 10 to the power of negative 34 seconds ago are now 2 meters apart. 2 points that were 1 meter apart 10 to the power of negative 33 seconds ago are now 1,000 meters apart. The space between them has not been filled by new material flowing in from outside. The space has simply grown, in the intrinsic geometric sense, because the metric that defines distances has expanded. This is the same kind of growth that drives the expansion of the universe we observe today, the slow, accelerating expansion that carries distant galaxies away from us and produces the cosmological redshift of their light. But the rate in the inflating background is incomparably faster. The Hubble constant in our current universe, the rate of expansion we observe today, corresponds to a doubling timescale of roughly 10 billion years. The Hubble rate in the inflating background corresponds to a doubling timescale of 10 to the power of negative 34 seconds. The ratio between these two timescales is approximately 10 to the power of 50. The inflating background is expanding roughly 10 to the 50th power times faster than the universe we inhabit is expanding today. From inside the inflating background, if any observer could exist there, which by the dynamics of the inflating phase they could not, the expansion would not look like motion through space. It would look like the space itself stretching, carrying everything within it apart. There is no perspective from outside, the inflating background from which the expansion appears as motion through a larger arena. The inflation is the geometry, not something happening within a geometry. This distinction between inflation as motion through space and inflation as a change in the geometry of space matters for understanding what the still-inflating background is. It is not a region of space located somewhere specific that we could in principle point to, if only our telescopes were powerful enough. It is a set of regions whose geometry is evolving in a specific way, regions where the metric is expanding exponentially, where the energy density is dominated by inflaton field potential energy, where the conditions for eternal self-reproduction are met. The eternal inflation prediction is not that there is a special place in space where inflation is still happening. It is that there are regions of space-time regions that exist in the continuous manifold of space and time that our observable universe is embedded within, where the inflationary phase has not yet ended, and those regions are, by the dynamics of the theory, exponentially more numerous than the regions like ours, where inflation has already completed. There is an analogy that sometimes helps, though like all analogies it eventually breaks down. Imagine the eternally inflating background as an enormous, churning foam, not foam in the sense of soap bubbles on water, but a space-time foam, a structure in which the geometry itself is in constant violent expansion, while occasional regions of stability nucleate within it and grow into something quieter and more ordered. The foam is the inflating background. The stable regions are the post-inflation bubbles, the big bangs, the universes with ordinary matter and radiation, and eventual stars and planets. The bubbles nucleate within the foam, expand, and become the arena for whatever cosmological history their particular inflaton field configuration allows. From inside our bubble, the foam is invisible. We see our own stable, quieter, expanding universe. We see the gentle acceleration driven by dark energy. We see the cosmic microwave background, the large-scale structure, the galaxies and stars, and the long, slow future of our patch. The foam that produced our bubble and continues to produce other bubbles is outside our event horizon, outside the causal boundary, beyond which no signal from the foam can reach us. But the foam is not in our past. This is the critical point that the standard telling of the inflation story obscures. The standard narrative of cosmological history places inflation firmly in the past. Inflation happened in the first fraction of the first second, then it ended, then the hot Big Bang followed, then matter-dominated expansion, then structure formation, then stars and galaxies, then us. Inflation is the opening chapter, already closed, belonging to the early universe, in the same sense that the formation of the first stars belongs to the early universe as a completed historical event that produced the conditions we now inhabit. Eternal inflation dissolves this narrative. Not for our local patch within our observable universe. The inflationary phase did end approximately 13.8 billion years ago, and everything since has followed from that ending. But for the universe in the broader sense, for the totality of what exists, including the regions beyond our event horizon, the inflationary phase has not ended. It is ongoing. Right now, while you process these words, the inflating background beyond our event horizon is in the same phase that our observable region was in before the inflationary exit that we call the Big Bang. The first fraction of the first second of our universe's history has not ended globally, it ended here. It is still happening there, just past the boundary we cannot cross, in regions that will never send us a signal that arrives. Consider what this means for how you should orient yourself in time as well as in space. We discussed in the chapter on eternal inflation the asymmetry between the finite past and the unbounded future of the inflating cosmos. The inflating background has a beginning, the Border-Guth-Vilenkin theorem requires it, but it has no end. At every moment in the future, there is more inflating volume than there was before. More bubbles have nucleated. More post-inflation patches have been added to the ensemble. The process is not converging toward a completion, it is diverging away from one. In this frame, the present moment, the 13.8 billion years since our local Big Bang, the current state of our observable universe, is extraordinarily close to the beginning of the larger process. The inflating background began at some finite time in the past, and in the time since that beginning, our bubble has nucleated and run its cosmological history up to the present. But in the time available to the future, which is unbounded, the inflating background will produce a quantity of post-inflation bubbles so vastly larger than the current count that the current count is, in the relevant mathematical sense, negligible. We are not near the end of anything. We are not in the middle of anything. We are at the very beginning of a process whose extent in time has no upper bound. The engine has barely started. In the frame of what it will ultimately produce, there is a particular way of feeling the engine's operation that might help bridge the distance between the abstract description and something more immediate. At this moment, while you hold these words in your attention, the inflating background beyond our event horizon is doubling its volume every 10 to the power of negative 34 seconds. By the time a single neuron in your brain has completed a single electrochemical signal, a process that takes on the order of 1 millisecond, 1,000th of a second, the inflating background has doubled its volume approximately 10 to the power of 31 times. The volume of the inflating cosmos has increased in the time it took for one thought to complete its journey across one synapse in one brain, by a factor whose size cannot be written in standard notation. This is not a figure of speech designed to evoke awe. It is the literal technical content of the theory, applied to the doubling timescale of the simplest inflation models and the timescale of neural signal propagation. While you were processing the previous sentence, more inflating volume came into existence than all the matter in the observable universe could fill. While you process this one, more again. The engine does not require your attention. It does not require any observation. It does not respond to the presence or absence of observers within the bubbles it produces. It simply runs by the dynamics of the inflaton field in the high potential regions on timescales that have no relationship to any process accessible to human experience, producing volumes of space that have no relationship to any quantity accessible to human intuition. Now add the bubbles. Within the exponentially expanding inflating background, post-inflation bubbles continue to nucleate at a rate per unit inflating volume per unit time that is determined by the dynamics of the inflaton field. The rate is small. The probability of a bubble nucleating in any given Hubble volume-sized region of the inflating background in any given Hubble time is much less than 1. But the total number of Hubble volume-sized regions in the inflating background is growing exponentially. The total rate of bubble nucleation across the entire inflating background therefore grows exponentially with time, even as the rate per unit volume remains constant. Each bubble that nucleates is a local Big Bang. The energy stored in the inflaton field within the nucleating region converts into ordinary particles and radiation. The temperature surges, quarks and gluons form, protons and neutrons condense. Nuclei assemble in the first minutes of the bubble's thermal history. Atoms form hundreds of thousands of years later, when the temperature drops far enough. Gravity pulls matter together over hundreds of millions of years, forming the first stars and the first galaxies. Planets form around some of those stars, on some of those planets, in some of those galaxies, in some of those bubbles. Conditions arise that permit the assembly of the complex chemistry we associate with life. This is not speculation about what might happen in other bubbles. It is the straightforward application of the same physical processes we understand from our own bubble's history. The details differ between bubbles. The specific value at which the inflaton field settled, if the potential landscape has multiple minima, can produce different values of the physical constants, different particle masses, different strengths of the fundamental forces. Some bubbles may have physics incompatible with the formation of complex structure. Others may have physics that permits structure but of a radically different character from what we know. And some, by the statistics of an infinite ensemble, will have physics essentially identical to ours, producing cosmological histories essentially identical to our own, containing the full level I recurrence of identical Hubble volumes we examined in the previous chapter. The engine produces all of this, not intentionally, not purposefully, not with any goal or direction or preference for one outcome over another. The engine is a set of differential equations governing the behavior of a quantum field in a dynamically expanding spacetime. The equations produce what they produce. The bubbles nucleate where and when the field dynamics permit. The physics inside each bubble is set by the field configuration at the moment of nucleation. The rest follows from the laws of physics operating within the bubble, whatever those laws turn out to be. There is one final thing to add to this picture. before we close the chapter on the engine itself. The engine's operation is, in an important sense, happening at no distance from you. That statement requires unpacking because it sounds paradoxical. We have spent considerable time establishing that the inflating background is beyond our cosmic event horizon, at proper distances greater than 16.5 billion light-years. In what sense is something at that distance happening at no distance? The sense is this: the event horizon is not a location in space. It is a feature of our causal relationship to distant regions. The inflating background beyond the event horizon is not separated from us by a gap in space. There is no empty zone between the edge of our observable patch and the beginning of the inflating background, no region that contains nothing and serves as a buffer. The space-time manifold is continuous. Our observable patch is embedded within the larger space-time without any discontinuity at the event horizon boundary. The event horizon is a surface defined by the causal structure of the space-time, by which signals can reach which destinations in the expanding universe, not by any physical property of the space itself. If you could somehow be instantaneously transported to the edge of our event horizon, to a location 16.5 billion light-years from here, and look outward, you would see more space extending beyond you. You would not see a wall. You would not see the edge of anything. You would see more galaxies, more structure, the continuation of the cosmic web. And just past your new horizon at 16.5 billion light-years from your new position, you would again find the causal boundary beyond which the signals from the inflating background cannot reach you. The inflating background is not over there, in some remote corner of the universe. It is everywhere beyond the event horizon, which is a sphere centered on every observer in every post-inflation bubble. It is the immediate surroundings of our bubble, in the geometric sense, that the foam is the immediate surroundings of every bubble it contains. The distance is causal, not spatial. The engine is as close as causality allows anything beyond the horizon to be, which is to say, it is as close as something can be while being entirely beyond reach. The engine that made us is still running. The engine is running right now, in the space-time immediately adjacent to ours, separated from us not by a vast spatial gulf but by the structure of causality in an accelerating universe. The engine does not know we are here. The engine does not care that we are here. The engine is simply doing what the inflaton field dynamics require it to do in regions of space-time that will never exchange a signal with our region at rates that make the entire history of our observable universe look like a momentary fluctuation in an ongoing process without foreseeable end. We have named the engine. We understand its mechanism. We know why it runs and why it does not stop. What remains is the question of what it means, not technically, but in the full human sense of that word, to live inside a universe that is doing this. To be one of the engine's outputs, to sit in a chair on a planet in a bubble, while the process that produced the bubble continues its work in the space-time next door. That is where we close. That is where we have been heading since the first sentence of this video. Let us go there now. We have arrived at the reframe this entire video has been building toward. Everything that came before the Planck measurement, the inflation story, the eternal self-reproduction, the cosmic event horizon, the cold spot in Eridanus, the 33 physicist defense, the level 1 copies, the named engine, all of it was structural preparation for a single conceptual move. A move that changes not what you know about the universe, but how you hold what you know. A move that shifts the grammar of the largest claim modern cosmology makes about the nature of space and time. The move is this. Infinity is not a noun, it is a verb. When the word infinite appears in ordinary conversation about the universe, when a journalist writes that the universe is infinite, or a textbook states that a flat universe extends without bound, or a physicist says that the eternal inflation background has infinite volume, the word functions, grammatically and conceptually, as a noun. It names a property. It says that the universe is in possession of a particular attribute, the way a mountain is in possession of a particular height, or a lake is in possession of a particular depth. Infinite is what the universe is. Infinity is something the universe has. This grammatical framing carries a specific set of implications. It implies that the infinite extent of the universe is a fixed feature of a completed object, that somewhere out there the space extends without limit, and has always extended without limit, and will continue to extend without limit, in the same way that the mountain has always had its height and will continue to have it. The infinity is a static property. It is not something the universe is currently producing or actively generating. It is simply there, as an attribute of the space that already exists. The eternal inflation picture makes this framing wrong, not approximately wrong, structurally wrong, wrong in the grammar as well as the content, because the universe, in the eternal inflation picture, is not an object that possesses the property of being infinite. The universe is a process that is actively generating infinity, right now, at every moment, in the inflating regions beyond our event horizon. The infinity is not a feature of what already exists. The infinity is the cumulative result of what the engine continues to produce. It is not a noun, it is a verb. It is something the universe is doing rather than something the universe is. The distinction between these two framings is not subtle once you see it, but it is easy to miss because the noun framing is so deeply embedded in how we talk about space and size and the large-scale structure of the universe. Every analogy we reach for the universe as a container, space as an expanse, infinity as a place you could travel to, if you could travel forever, carries the noun framing implicitly. We picture infinity as a destination that keeps receding. We picture the universe as a stage on which events occur. We picture space as a medium that exists and within which things happen. Eternal inflation replaces this picture with one in which space is not a pre-existing medium, but an ongoing production. Space is not the stage. Space is the performance. The geometry of the universe is not a fixed backdrop against which cosmological history unfolds. It is something that is being generated continuously by the dynamics of the inflaton field in the regions where inflation has not yet concluded. The universe is not big in the way a room is big, because a room is a fixed object with a fixed volume that exists whether or not anything is happening inside it. The universe is unfinished in the way a fire is hot, because the heat is not a property the fire possesses independently of the burning, but something the fire produces by continuing to burn. Let us develop this analogy carefully, because it carries more of the content than it might initially appear to. A fire burning in a hearth is not a state. It is a process. The wood is not on fire in the way a book is on the shelf, as a static relationship between an object and a location. The wood is burning. The burning is a chemical reaction, an ongoing transformation of molecular structure, a continuous release of energy as the carbon bonds in the wood break and recombine with oxygen to form carbon dioxide and water vapor and heat and light. The fire is what the wood is doing, not what the wood is. Stop the process, and the fire ends instantly. There is no residual fire left in the cold ash after the burning has stopped. The fire was not a thing that the wood had and then lost. The fire was the burning, and when the burning ended, the fire ended with it. The heat dissipates, the light fades, the process is over. The infinity of the universe in the eternal inflation picture has exactly this character. It is not a property the universe possesses independently of the ongoing inflationary process. It is what the process produces by continuing to run. If the inflationary process were to stop, if some mechanism existed that terminated the exponential expansion in the inflating background globally and simultaneously, the result would not be an infinite universe that persisted without the ongoing production. The result would be a finite collection of post-inflation bubbles embedded in a space-time that had stopped producing new volume. The bubbles that already existed would still exist, but no new inflating volume would be generated. No new bubbles would nucleate, and the total spatial extent of the resulting cosmos, however vast by any ordinary measure, would be finite. The infinity requires the ongoing process. The process is the infinity. Stop the process and the infinity stops. This is what the verb framing means. Infinity is what the engine produces by running. It is the present tense output of a present tense activity. And the activity, in the eternal inflation picture, has no off switch. The engine runs because the dynamics of the inflaton field in the high potential regions continue to sustain inflation. The engine will continue to run because those dynamics have no global termination mechanism. The infinity will continue to be produced because the engine will continue to run. The universe is not infinite. The universe is infiniting. Let us be specific about why the off switch does not exist. This is not a philosophical claim or an argument from the absence of evidence. It is a technical statement about the mathematical structure of the equations governing the inflaton field during inflation. Consider the simplest chaotic inflation model, the quadratic potential, in which the potential energy of the inflaton field is proportional to the square of the field value. As the field value increases, the potential energy increases. As the field value decreases towards zero, the potential energy decreases towards zero, and when the field reaches the minimum, the inflationary phase ends locally and reheating begins. In the classical description, the description that ignores quantum fluctuations, the field everywhere rolls monotonically downward toward the minimum. Given enough time, every point in the inflating space will see the field reach the minimum. Inflation ends globally. The entire inflating region converts to a post-inflation state. There is no eternal inflation in the purely classical description. Quantum mechanics changes this. The inflaton field is a quantum field. At every point in space, at every moment in time, the quantum uncertainty principle requires the field to fluctuate around its classical trajectory. The fluctuations are small compared to the classical motion in most circumstances. This is why the classical description is a good approximation for many purposes, but they are not zero. And the consequences of their not being zero, once you account for the volume dynamics of an exponentially expanding spacetime, are decisive. At any given point in the inflating background, there is a small but non-zero probability per unit time that the quantum fluctuation at that point pushes the field upward rather than downward. The probability depends on the shape of the potential and the current value of the field. For the quadratic potential and field values in the range relevant to inflation, the probability is small, much less than 1 per Hubble time per Hubble volume. The classical downward roll dominates at any individual point. But consider the population of all points in the inflating background simultaneously. At any given moment, there is some fraction of the inflating volume where the quantum fluctuation at that moment is pushing the field upward. Those regions, where the field value has increased rather than decreased, now have a higher potential energy than before. A higher potential energy drives faster exponential expansion. The volume of those regions grows faster than the volume of regions where the field is rolling downward. In the next moment, the upward fluctuated regions occupy a larger fraction of the total inflating volume than they did in the previous moment. The key calculation is the comparison between two rates. The rate at which inflating volume is being converted into post-inflation bubbles by the classical downward roll, and the rate at which inflating volume is being added by the exponential expansion of the upward fluctuated regions. If the second rate exceeds the first, if the inflating background grows faster than the bubbles consume it, then inflation is eternal. The inflating background never shrinks to zero. It grows forever, with bubbles continuously nucleating within it. For the quadratic potential, and for a broad class of other slow-roll potentials, this calculation comes out in favor of eternal inflation. The growth rate of the upward fluctuated regions, compounded by the faster expansion those regions undergo, exceeds the depletion rate from bubble nucleation. The inflating background grows. Inflation is eternal, not as an assumption, as a derived result of solving the dynamics. The quadratic potential is, as we noted in the chapter on inflation, disfavored by current observations of the tensor-to-scalar ratio. The Planck and bicep Keck measurements of the CMB polarization have constrained the tensor-to-scalar ratio tightly enough to rule out the simplest large-field inflation models, of which the quadratic potential is the canonical example. But the conclusion of eternal inflation does not depend specifically on the quadratic potential. It arises across a wide range of slow-roll potentials, including the plateau potentials and Starobinsky-type models that are currently favored by the observational constraints. The specific calculation differs for different potential shapes, but the qualitative result that the upward fluctuated regions reproduce themselves faster than the downward rolling regions' complete inflation persists across the models that match the data. To get inflation without eternal inflation, to construct a model in which the inflationary phase terminates globally after a finite time, you need a potential that is steep enough everywhere that the classical downward roll always dominates over the quantum fluctuation upward push in every region at every moment. This requires a specific kind of potential shape that the current observational constraints do not require, and that the simplest theoretical considerations do not prefer. It is possible to build such models. They are not natural in the sense that they require additional structure imposed on the potential that goes beyond what the data demands. The simpler models, the ones that fit the data without additional structure, produce eternal inflation. The off switch, to avoid the eternal inflation result, must be deliberately engineered into the theory at the cost of theoretical naturalness. Most physicists are reluctant to pay this cost without observational motivation, and there is no observational motivation for it. The data does not require a global termination of inflation. The data requires only a local termination, the one that produced our Big Bang 13.8 billion years ago. The global behavior of the inflating background is not constrained by any measurement we can make from inside our bubble. In the absence of a reason to artificially terminate the global inflation, the equations are left to run as they naturally run, and as they naturally run, they produce eternal inflation. The math kept producing it. That sentence has appeared several times in this video. It will appear again in the closing. It appears here because the absence of the off switch is not a discovery someone made by looking for it. It is the absence of a feature that would need to be deliberately added to a theory that otherwise runs without it. No one chose for inflation to be eternal. No one designed the equations to produce eternal self-reproduction. The equations simply do not contain the mechanism that would stop it. And in physics, when the equations do not contain a stopping mechanism, the process does not stop. There is one more dimension of the verb framing worth developing before we close this chapter, because it bears on how we should feel about the universe we inhabit. The verb framing infinity as something the universe is doing rather than something the universe is implies that the universe has a direction, not a spatial direction, a temporal direction. The universe is not a completed object spread out in space. It is an ongoing process moving forward in time. At every moment, there is more universe than there was at the previous moment. The total volume of space, the integral of all the spatial geometry across the full extent of the inflating cosmos, is larger right now than it was when you began reading this chapter. It will be larger when you finish than it is now. It will be larger after you have gone than it will be when you finish. The universe is accumulating in the temporal direction at a rate that has no ceiling and no natural terminus. This temporal directionality of the universe's production of space is what the noun framing obscures. In the noun framing, the universe simply is infinite. It possesses an infinite extent as a timeless property, the way the integers possess their infinite cardinality regardless of when you examine them. In the verb framing, the universe's spatial extent is not timeless. It is growing. It was smaller in the past, not in the sense that the universe contracted and then expanded, but in the sense that the process had not yet produced as much as it will produce. It will be larger in the future, not in the sense that the existing space stretches, but in the sense that the process will have produced more. The infinity is the limit of this production process. As time extends without bound, it is not a property present at any finite moment. It is the asymptotic result of a process that has been running for a finite time in the past and will run for an unbounded time into the future. To say the universe is infinite, in the full awareness of what eternal inflation implies, is to say that the universe is in the process of becoming infinite. The process has a beginning, as the Bordeguth-Vilenkin theorem requires. It has no end, as the dynamics of inflation in the absence of a global termination mechanism require. The infinity is not yet complete. It is being produced. It will continue to be produced. The universe is not an infinite place. The universe is an infiniting process. And there is one final thing to add to this reframe before we let it rest and move into the closing chapter. Something quiet that the verb framing reveals when you hold it long enough. The process has no purpose. The infinity is not being produced for any reason beyond the mechanical operation of the equations governing the inflaton field. There is no goal toward which the production of new inflating volume and new post-inflation bubbles is directed. There is no destination the process is approaching. There is no completion it is working toward. The engine runs because the equations say it runs. The equations produce what they produce because that is what the mathematics of a quantum field on an exponentially expanding spacetime yields. The infinity is the residue of this production, not its purpose, not its goal, but its unavoidable byproduct. When this video's title says the universe is infinite for a reason, the word reason does not mean purpose. It means mechanism. The reason is not that someone or something intended the universe to be infinite. The reason is that the mechanism generating the universe, the inflaton field dynamics in the high potential inflating regions, has no off switch, and a generating mechanism without an off switch, running for an unbounded time, produces an infinite result. The reason is mechanical. The reason is mathematical. The reason is the absence of a termination condition in a set of differential equations that someone first wrote down in the early 1980s and that the universe has been solving ever since. The universe is not big. The universe is unfinished. And the unfinishing is not an accident or an oversight or a mystery. The unfinishing is what the equations do. In the closing chapter, we will bring all of this back to where it began. Back to the chair, the breath, the body, the specific moment of awareness you are inhabiting right now. We will ask what it means in the full human sense, not the technical sense, to live inside a universe that is doing this, to be one product of a process that has no stated purpose and no scheduled conclusion, to inhabit a bubble in a foam that is still foaming, a pause in an engine that is still running, a finished local patch of something that is globally unfinished. That is where we end, and the ending, I hope, will feel less like a conclusion than like the beginning of a longer silence in which the full weight of what the data says can settle. Let us go there now. We have come a long way from where we started. We started with the space immediately around you, the air between your hands, the gap between your shoulders and the wall, the cubic centimeters of atmosphere inside your chest as you drew a breath. We started with the observation that this space, unremarkable and invisible and taken entirely for granted, was once part of something undergoing the most extreme physical process our equations can describe. We planted a sentence before any of the structure had been built to support it. We said the engine that made us is still running. 12 chapters later, that sentence has a different weight. We have walked through what infinite actually means in the mathematical and cosmological sense, and why the colloquial picture of a very large universe gets the concept wrong in ways that matter. We have walked through the Planck 2018 measurement, the 4 years of satellite observation that produced the number 0 and the curvature of the universe flat to within half a percentage point, and through what that number implies, under the assumptions the working community treats as its operating default. We have walked through the inflation story from Guth's notebook realization in December of 1979, through Linde's slow roll refinement in 1982, through the 4 decades of precision confirmation that followed. We have arrived at Linde's 1986 paper, and the result he published because the equations required him to the result that the inflationary phase, once started, does not stop globally. We have looked at the cosmic event horizon, the boundary at 16.5 billion light-years that seals our observable patch from the still-inflating background surrounding it. We have examined the cold spot in Eridanus, the closest the observational record has come to a possible fingerprint of what lies beyond that boundary. We have watched the Idja-Steinhardt-Loeb critique and the 33-physicist rebuttal play out in the pages of Scientific American, and understood why the mainstream community defends eternal inflation not as a speculation but as a deduction from confirmed theory. We have followed the arithmetic of a flat infinite universe to its uncomfortable conclusion about the existence of other versions of your current physical state at finite distances across the infinite expanse of space. And we have named the engine, described its mechanism, explained why it has no off switch, traced the doubling of inflating volume on timescales that have no relationship to any process in ordinary experience. Now the question is what to do with the picture we have assembled. Not technically we have done the technical work, but in the fuller sense, what does it mean as a human being inhabiting a body on a planet, in a galaxy, in a bubble, to understand that this is the situation you are in? The first thing to say is that the cosmological picture does not reach the scale of your immediate life. The engine running beyond the event horizon does not affect what you will do tomorrow. It does not change the texture of the conversation you will have this afternoon, or the quality of the meal you will prepare this evening, or the specific weight of the decision you have been turning over in your mind for the past several weeks. Cosmology operates at a scale so far removed from the scale of human experience that the two rarely intersect in any practical sense. The universe being unfinished does not make your personal obligations unfinished in a different way. The infinity of the inflating background does not make your specific corner of the finite observable universe any less yours. This is not a small observation. It is easy to feel, after an extended encounter with the scale of the universe, that the scale somehow diminishes the personal. That knowing the universe is unfinished makes your own particular, finishing your own mortality, your own bounded span of attention and effort, seem less significant, as if significance required a universe of the right size to contain it. This is a mistake, and it is worth naming it as one. The scale of the universe is not a context that reduces the significance of individual experience. It is a context that sits alongside individual experience without erasing it. The two scales coexist. The engine runs on timescales of 10 to the power of negative 34 seconds. Human lives run on timescales of roughly 2.5 billion seconds. These scales do not compete. They simply occupy different registers of a reality, large enough to contain both. The second thing to say is that the picture does, in some quiet way, alter your sense of where you are. Not dramatically, not in a way that announces itself, but in the way that genuine understanding always alters the texture of perception slowly, subtly, without a specific moment of transformation, until one day the familiar looks slightly different than it did before. The room you are in is not a room in a finished universe. It is a room in one finite post-inflation bubble, embedded in an exponentially expanding inflating background that continues to generate new bubbles on timescales shorter than any process occurring within the room. The walls of the room are not the walls of reality. They are the walls of a room inside a bubble, inside a foam that is still foaming. The space you occupy is a small local result of a process operating at scales so far beyond the local that no analogy available to human cognition can bridge them without distortion. This does not make the room less real. It does not make the walls less solid, or the air less breathable, or the chair less supportive. It makes the room what it actually is, a specific configuration of matter that exists because a local region of the inflating background, 13.8 billion years ago, experienced a phase transition that converted inflaton field energy into ordinary matter and radiation, and because the subsequent cosmological history of that local region permitted the assembly of the specific chain of physical and chemical and biological complexity that eventually produced a room with a person in it attending to a recording about cosmology. You are here because the engine stopped here, long enough and in the right way for the stopped region to produce you. The engine has not stopped everywhere, it has stopped only here. And here, as a result, is the kind of place where things like rooms and chairs and attention and recordings about cosmology exist. The third thing to say concerns the copies, the level I recurrence, the infinitely many other physical configurations identical to your current state distributed across the infinite flat universe the Planck measurement describes. The mathematics says they exist. The cleanest reading of the data says they exist. And there is a particular way to carry this that is neither denial nor despair. The copies exist at distances so far beyond any conceivable human reach that in every practical sense, moral, emotional, relational, experiential, they might as well not exist. They cannot affect your choices. They cannot share your experiences. They cannot relieve your losses or amplify your joys. They are isolated inside their own causal spheres, the way you are isolated inside yours, each experiencing what feels from the inside like the singular and unrepeatable fact of being a particular person in a particular moment, each unaware of the others in exactly the way you are unaware of them. The existence of the copies does not mean your experience is not real. It means your experience is not rare. There is a difference. The experience you are having, the specific quality of attention you are bringing to these words, the particular angle of your thoughts about what you are hearing, the specific emotional register in which the ideas are landing is real, in every sense that the word real applies to. It is happening. It is yours. It is, at the scale of your causal sphere, genuinely singular. The copies do not diminish this. They simply extend it, replicate it, without your knowledge and without effect on you, across the infinite expanse of a flat universe with uniform physics. What the copies do, if anything, is shift the emotional register in which you hold your own existence, from unique to typical, from irreplaceable to infinitely reproduced. This shift is uncomfortable, and the discomfort is real, but it does not undermine the significance of this specific instance. You are not less you because there are infinitely many others with the same configuration. You are simply one instance of a configuration that the mathematics of the universe produces infinitely many times. This instance is the one that experiences itself. That experience is not shared with the others. It belongs to here, to now, to this particular crossing of attention and physical state that constitutes a moment of awareness. The universe contains infinitely many of these crossings. You are one of them, the one you are. The fourth thing to say is that you are extraordinarily early. We discussed this in the context of eternal inflation, the asymmetry between the finite past and the unbounded future of the inflating cosmos, and what it implies about the statistical position of observers who exist as early in the process as we do. But it deserves to be said again here, in the closing, because the implications of being early are different from the implications of being late in ways that matter for how you orient yourself toward the future. To be late in a process is to be near its completion. To be late is to inhabit a world in which most of what the process will produce has already been produced, and what remains is the tail end, the diminishing returns of a process approaching exhaustion. To be late in the universe, in the way we are accustomed to imagining ourselves as being, is to live in a mature cosmos, far from its violent beginnings, surrounded by the long-established structures that the early universe produced, and that will slowly wind down over the cosmic timescales ahead. To be early is different. To be early in the eternal inflation process, and we are, by the statistics of an unbounded future, extraordinarily early, is to exist at a moment when the vast majority of what the process will ultimately produce has not yet been produced. The bubbles that will eventually nucleate in the inflating background, the post-inflation cosmological histories that will eventually unfold, the forms of complexity that will eventually emerge in those histories, almost none of this has happened yet. We are, in the frame of what eternal inflation will produce, in the very opening pages of a story whose total length is without limit. This is a strange orientation to adopt. It feels wrong, because everything about our observable universe suggests lateness. 13.8 billion years of accumulated history. Stars evolved through multiple generations, elements synthesized and distributed and incorporated into planets and biospheres. The universe we inhabit is old by any ordinary measure, but in the frame of the eternal inflation process that contains our bubble is a recent event. The process that produced it has barely begun producing. We are not the culmination of anything. We are an early chapter in something without a final chapter. The fifth and final thing to say, the one that carries the most weight, the one that the engine named in full makes possible to say clearly, is the one this video has been building toward from its first sentence. The engine that made us is still running. We are here because of a process that has not ended. The same physical mechanism that produced our local patch, the inflaton field dynamics, that drove the exponential expansion of the region that became our observable universe, that seeded the density fluctuations that became the large-scale structure that produced the smooth, flat, monopole-free post-inflation universe that subsequently evolved into the cosmos we inhabit. That mechanism is operating right now. in the space-time immediately adjacent to ours, separated from us by a causal boundary rather than a spatial gulf, doubling the volume of inflating space on timescales shorter than any process in our experience. We are not the products of a completed creation, we are the products of an ongoing one. The creation did not finish when our bubble nucleated. The creation did not finish when the first stars formed in our bubble, or when the solar system assembled, or when life emerged on this planet, or when a species capable of reconstructing the history of its own origins arose on that life-bearing planet. The creation is still in progress. Not here. Here it has been running in the post-inflation mode for 13.8 billion years, but everywhere else, in the inflating background that produced here, and continues to produce other heres beyond our event horizon. There is something in this that is neither consoling nor threatening but simply accurate. The universe is not done with the business of producing universes. It is in the middle of that business right now. Our universe, our bubble, our observable patch, our local cosmological history is one unit of production in a production process that will continue indefinitely. We are finished, in the local sense. The inflating phase ended here. The post-inflation expansion has been running for 13.8 billion years and will run for an incomprehensibly longer time into the future, ending eventually in the cold, dark, thermodynamically exhausted state that cosmologists call the heat death of the local universe. But finished locally does not mean finished globally. Globally, the process is nowhere near finished. Globally, the process has no scheduled finish. Let us come back, at the very end, to the space immediately around you, the air between your hands, the gap between your shoulders and the wall, the volume of atmosphere inside your chest right now, at the depth of a breath. That space was once part of a region undergoing the exponential expansion of the inflationary phase. The expansion ended here. The energy of the inflaton field converted into the quarks and gluons of the early universe, which cooled into protons and neutrons, which fused into the nuclei of the light elements, which were dispersed into the cloud that eventually became the solar system, which condensed into the sun and the planets, which over 4.5 billion years of chemistry and geology and biology produced the air you are breathing and the body breathing it. The space you occupy is a specific local result of a chain of events that began with a phase transition in a quantum field and will end on the timescale of the sun's death with the vaporization of the planet on which all of this occurred. Between that beginning and that end, there is this: a moment of awareness, a body in a room, an attention brought to bear on the largest question a mind can hold, the question of what kind of place this is, what kind of process produced it, what kind of process is still producing others like it, beyond the boundary of what can be seen. The question has an answer. The answer is precise. The answer is confirmed by the most sensitive cosmological measurements ever made and defended by the community of physicists who made them. The answer is, this is a bubble in an inflating foam. The foam is still inflating. The bubble is one of an unbounded number of bubbles that have nucleated and will nucleate in the inflating background. The bubble is finite, isolated, evolving, according to the physical laws that obtained when the inflaton field transitioned out of the inflationary phase in this region. The bubble is, in the frame of the larger process, extraordinarily young. The bubble contains, in the full extent of its infinite flat interior, an infinite number of configurations identical to every configuration that has ever existed within it, including the one you occupy right now. And the process that produced the bubble is running, right now, on the other side of a causal boundary at 16.5 billion light-years, doubling the volume of inflating space every 10 to the power of -34 seconds, producing new bubbles at a rate that grows exponentially with time, continuing without any termination mechanism in the equations that govern it. The terrifying thing the title of this video promised is now, I hope, clear, and perhaps, after the long journey through the structure that supports it, slightly less terrifying than it seemed at the outset. Not because the picture has been softened. It has not been softened. The picture is what the picture is. But terror, when it is produced by genuine understanding rather than by ignorance or surprise, tends eventually to settle into something else, into recognition. into the specific quality of attention that comes from knowing, as precisely as current knowledge permits, what kind of thing you are and what kind of place you are in. You are a specific configuration of matter, one that exists in one post-inflation bubble, produced by a process that has not ended, at a moment early in the larger history of that process, at a location in an infinite flat space, populated by infinitely many configurations identical to yours, surrounded by an event horizon beyond which the engine of inflation continues to operate at rates no comparison to ordinary experience can make intuitive. You are, in the full sense of the word, a product of the process, not a byproduct, not an accident. A product, something the process generates by operating according to its dynamics in a region where the physical constants happen to permit the assembly of complex structure. You are what the equations produce when they produce a universe like ours. You are one instance of what a post-inflation bubble with the right conditions eventually generates when it runs long enough. The process does not know you exist. The engine has no awareness of its products. The inflaton field dynamics that continue to operate beyond our event horizon carry no record of what they have produced here, and no preference for what they will produce elsewhere. The process is indifferent, not in the way a person can be indifferent with awareness and the choice not to engage, but in the way a physical law is indifferent, which is to say, with no awareness at all. The equations run, the volumes grow, the bubbles form, the cosmological histories unfold, and somewhere in one of those histories, on one ordinary planet orbiting one ordinary star, in one ordinary galaxy near the edge of one ordinary bubble, a body sits in a room and directs its attention toward the question of what is happening beyond the boundary it will never cross. That is you, right now, in this moment. The engine does not need you to understand it in order to run, but you are here, and you do understand it, or something approaching it, something closer to understanding than any generation before yours had access to. The Planck satellite existed, the measurements were made, the mathematics was worked out, the 33 physicists wrote their letter, the inflation community defended its prediction, the data accumulated across 4 decades of increasingly precise observation. And now, in this moment, a mind, your mind, holds the picture they produced. That is not nothing. A universe that contains minds capable of measuring its curvature, tracing its history back to the first fraction of the first second, deriving the existence of a still-inflating background from the dynamics of a quantum field, calculating the distance to the nearest identical copy of every configuration of matter within their observable patch that universe is, in a specific and non-trivial sense, doing something that the inflating background beyond the event horizon is not doing. The inflating background is producing volume. Our bubble is producing comprehension. These are not equivalent accomplishments. The volume production is faster, vaster, more relentless, operating on timescales and scales that comprehension cannot match. But comprehension is the thing that can reflect on the volume production and know it for what it is. The inflating background cannot know itself. Our bubble, this bubble, the one you are in, can. That is extraordinary. It is temporary, and in this moment it is ours. Somewhere beyond the cosmic event horizon, at a proper distance of 16.5 billion light-years from the chair you are sitting in, the inflaton field sits at a high value on its potential landscape. The metric of the surrounding space doubles every 10 to the power of negative 34 seconds. New bubbles nucleate within the inflating background at a steady rate. New cosmological histories begin. New volumes of post-inflation space accumulate. The total extent of the inflating cosmos grows by amounts that make the observable universe appear, in the relevant mathematical comparison, as nothing at all. The engine runs. It ran before our bubble formed. It ran while our cosmological history unfolded. It is running now, in the moment you hold this thought. It will run after the last star in our local group has exhausted its fuel, after the last black hole in our observable patch has evaporated through Hawking radiation, after the last organized structure in our causal sphere has dissolved into the thermal equilibrium of a universe that has reached its maximum entropy. After all of this is done, and there is nothing left within our event horizon, but the cold quantum noise of an exhausted cosmos. The engine will still be running, somewhere beyond the horizon, on the other side of the causal boundary that no signal we will ever send can cross, producing new bubbles and new histories and new moments of awareness in new patches of post-inflation space that will never know we existed and whose existence we will never know. The universe is not big. The universe is unfinished. The engine that made us is still running, and we are right now in this specific and unrepeatable crossing of physical configuration and momentary awareness, one of the things it has made.